Okay, so hey, Zhiting, Eric.
Hey, Zhiting, Eric.
Yeah, so should we do a quick test, maybe like screen sharing or something?
I think
I'll make you as co-host.
Right. Let's see. I have the tutorial up on my screen. Let's see if I'm able to share it correctly. Okay, do you all see my?
Yeah.
Right, and let's try to enter presentation mode. Okay, does it show properly in the presentation mode?
Yeah.
Okay.
Yeah. Right.
Okay.
Let me share. And that will be presenter. Okay, did you see everything okay?
Yeah, looks good.
Looks good.
Yeah, cool.
Okay, then let's see. Zhiting, did you save anything since this morning?
Yeah, I saved one small change, but it's okay. We can revert if there's problems with the file, right?
Yeah, I have something, but I was afraid of saving because I may erase yours, so I didn't save.
It's all right. The things I will do are very minor polish. It won't affect me if you revert.
So do you think I should just? I mean, again, it's very minor thing. It's just the scripts that.
Okay, then why don't you just go ahead and save? If there's a problem, we will revert to your version. How about that? Yeah, go ahead and save yours. I think it should be no problem.
I should save.
Yeah,
okay.
You should save.
Yeah.
I won't touch anything.
Okay. So then, are you sure? I don't need to save, but I can, of course, just save some little text.
Yeah, I'm sure about it because I actually have a separate copy of my changes down on my notepad. So
okay,
if I need to restore, I could always do it later.
Yeah, because you can also present from your deck, because I only made change in that scope that I'm presenting.
Exactly, right. And my changes are only in my scope.
Yeah, and then we can integrate afterwards.
Yeah, I think that's the best choice.
Yeah.
It is going to make a change. So I will stop sharing, reopen.
Got it. Okay, I'll try to pick up the changes.
Yeah. So in the QA session, so would you like to so we basically encourage the audience to post questions in the chat box. So would you like to say check these questions by yourself, or I can read the questions?
I think if it's the QA session, you need to read a question to the others. Other you will be the moderator, for example, and then and then the audience can hear basically what is asked.
Yeah.
Right. Okay. Let me see. I'm refreshing that.
Let me try sharing my screen.
Yeah.
You see the slides?
Mm-hmm.
Presentation.
Looks good.
Yeah. Okay. Cool.
Okay, so my Dropbox is still synchronizing. Let's see. Okay, so I'm going to freeze here and use my current version.
Got it. Yeah, then what I'll do is I will, when I get your version, I'll pick it up, make my own local copy and do the little bit of polishing I wanted to do.
Okay. Let's see, what should I do? I will do the okay. So then anything else?
Yeah, I think it's pretty much
One thing I noticed was when we are done with the presentation and into the QA, it may be better to stop sharing the screen so that our faces will be actually appear on the main screen. Otherwise, it's hard to yeah. That's just a suggestion, but maybe this is okay because we're not letting everybody in the room, right? So we actually could see each other. Because in my last talk, when people are asking question, we're not going to be able to see them. So this time, I don't know. None of them. Are we going to allow audience to directly ask questions?
Yeah, I think they can unmute themselves to ask questions.
Yeah, actually.
Or like, yeah, they can or like raise the hand and we
okay.
can.
Yeah. Yeah. Then in that case, I think it's better to stop sharing so that the audience can see basically the person who asks questions.
That makes sense. Okay, so our protocol is if there's a question that happens in the tutorial or the QA, we'll stop sharing to
only in the QA. During the tutorial, of course, you don't stop, right?
Okay, so just QA makes sense to me.
QA basically is you stop using the slides at all, right? So that's where you can turn off the slides.
That sounds good.
Okay. I think also during presentation, probably you don't want to unmute people because that will be too noisy. Yeah. Let's just, in case people raise hands, you can choose to respond or not respond. Usually I don't because it's hard to even see all of them. It's distracting. Okay.
Right. I think for me, on my part, at least the way I'll do it is I'll encourage the audience to type their questions and we'll address them all as a group at the end during the QA. So it's just given the way Zoom works, right? I think that's going to be more less disruptive to everybody in the room.
Yeah.
Yeah, sounds good.
Okay, we have another 20 minutes. By the way, how many people are in our session today? Do you know?
Not sure yet. So the maximum number of audience like 500. They say the upper limit. But we don't know like how many will join.
Yeah, I mean, how many registered to us? Do you have that number?
No, I don't think we have this number.
I see. Oh, it is already recording. I don't know.
Yeah, it's recording like starting from actually 7 a.m. today. Actually, so.
I see. Well, can I stop it? Because right now, I don't think we need to record that.
No, we can't stop it. It's automatic. Okay, so yeah, probably let's get started. So hi everyone. Yeah, welcome to the KDD 2020 tutorial on learning from all experiences, a unifying machine learning perspective. I'm very excited to give this tutorial with amazing speakers, Qilong Guo and Eric Xing from Carnegie Mellon and Petuum. So in this tutorial, we are going to present a systematic, unified perspective of machine learning with all types of experiences that involve a large volume of different machine learning paradigms. And we will discuss the theoretical foundations of this and its operationalization for like productive machine learning solution design and development in support of different applications at scale. Okay, so a little bit about the presenters. So I'm Zhiting, a PhD candidate at Carnegie Mellon and a research scientist at Petuum. And I'm joining UC San Diego as an assistant professor next year. And Qilong is the co-founder and the CTO at Petuum. And Eric is a professor at CMU and the co-founder chief scientist at Petuum. And we also would like to acknowledge some people from Petuum and CMU who have contributed to this tutorial, including Ulrich, Hao, Hector, and Willie. Yeah, so let's begin with some broad context. So these days, people are expecting AI and machine learning to do a lot of things, ranging from like autonomous driving, machine translation, dialogue systems, to healthcare and scientific studies in biology and other domains. So machine learning is about the computational method that enable machines to learn concepts from experiences. And the applications we just saw each come with different type of experiences, such as a collection of data examples, or like structured constraints that encode our knowledge about the problem of interest. Or maybe the agent can interact with the environment to receive the reward signal to guide the training. And in some cases, we may have access to auxiliary agents for co-training of the agent of interest, or even adversaries that compete with the target agent. Okay, so oftentimes, these problems can present not just a single type of experience, but instead a combination of different type of experiences. And with all these distinct type of experiences, and especially arbitrary combinations of them, in practice, it's often very difficult to design machine learning solutions to deal with the experiences and make full use of them for efficient learning. Because the experiences are in different forms, having different behaviors, and posing huge complexity to modeling, learning, and analysis. So here's a concrete example in machine learning for healthcare. In an emergency room, a massive array of devices is used to measure the patient and generate a large amount of data and signals in different forms. So you can imagine it's very difficult, if possible at all, for an AI agent to consume all of the signals for training and inference and make decisions accordingly. So this is a typical real healthcare problem, which is very different from, for example, an academic well-crafted benchmark, where we are presented with clean single type of labels, and we can simply train a neural network on it. A ready-to-use AI solution is extremely complex, given all these experiences to train on. For example, here's a concrete example where we were asked to produce medical reports of patients based on the radiology data and the images. And this whole process has to be integrated into the doctor's workflow. That means simply having a standalone simple program that is trained on image labels is not going to be adequate. Instead, what we really need is a full pipeline of solutions which understands the images and the text and integrates the rich healthcare knowledge and constraints, and accordingly generate accurate reports. So the creation of such a for complex algorithmic solution obviously is out of the reach of the current so-called AutoML that does automatic search of hyperparameters or neural architectures. And furthermore, even if you develop an algorithmic solution, this is still not enough. To make the solution ready to use in the real workflow, it's necessary to deal with the interoperation with a lot of other underlying components. For, say, management of data and the different experiences, and the distributed training of models, probably on like heterogeneous hardware like CMU, like a GPU and the CPU, where one has to like probably handle computation and communication. And the other aspects like resource scheduling, because other jobs could also share the same resources in the computing environment. And also like for the recovery and so on and so forth. So an AI solution, as we see it, is only the tip of an iceberg. All these different aspects of computing are interconnected and interact with each other. Together complete a task of interest. Okay, so how do we handle all of these aspects and components to get a full AI solution? The current way people are doing is mostly like crafting. We tend to design bespoke solutions for individual problems. For example, every time given a new problem to deal with the particular set of experiences presented in the problem, people would often create specialized learning procedures. And this is often depending on their familiarity with different machine learning algorithms. And given different computing resources, people have to, like say, craft different distributed training strategies and the resource management schedules. And the whole process is often not very reusable. So given 100 problems, we may need 100 bespoke solutions. So how can we move machine learning or AI into a discipline where one can build solutions capable of learning with all experiences for a broad spectrum of problems under the guidance of a unified and systematic perspective, and built in a standardized, reusable, repeatable, and reliable way? Just like in the aviation industry, people use repeatable building blocks and assemble an aircraft in a principled and systematic manner. And once an aircraft is built, many aircrafts can be built in the same way. So this leads to our tutorial today. And here's the outline. This tutorial basically consists of 3 parts. The first part is presented by Eric. It's about theory for a standard equation that provides a unified mathematical formulation for learning with all experiences in all learning paradigms. And in the second part, I will be talking about tooling for operationalizing the framework and enabling easy composition of machine learning solutions. And the third part by Qilong is about computing infrastructures for productive machine learning, including interoperation, automatic tuning, distributing, and scheduling. And there will be a 20 minutes QA and a break between each part. During the talk, if you have any questions, please feel free to post your questions in the Zoom chat box, and the presenter may be able to answer during the talk or in the QA session. Okay, so I will stop here, and so that Eric can take over. So Eric, you are muted.
Can you all see my screen now?
Yep. Cool.
Okay, great. Yeah, thanks, Zhiting, for the very thorough introduction. As you can see, the audience, you can see from his introduction, we are dealing with a very large problem space of, learning, from all experiences and dealing with all different kinds of tasks. To give a tutorial that covers exhaustively and comprehensively all the methods people have invented so far would be really, really challenging within even the entire 4 hours. Maybe even a semester wouldn't be enough, right? And particularly if each time you run into a new problem and you have to do the following and do a lot of, new programming, design, and implementation, that would really, really make your life very miserable. So what we plan to do is to begin by presenting a theoretical framework that allow the production of a blueprint that people can use to hopefully mechanically compose solutions of different kinds from a catalog of ideas and building blocks, and therefore make the solutions more reusable, more explainable, and also more robust. So with that, we're going to begin, some background knowledge. As you can see, nowadays, model development and the solution development in machine learning and AI is really becoming a very, very intense competitive sports. You can see that this is indicated by the ever increasing size of the models, as we see, going all the way just in the past few years from a few million parameters to a few billion or even hundreds of billions of parameters, as we see recently in GPT-3. And also the complexity of such models are really, really, huge and daunting, right? And also it is worth noting that even for such a big model, usually they are each trained from a single source of experience. And they are also extremely data hungry, right? And there are some problems with these type of solutions and approaches, as I listed in here. First of all, these models are complex, as I said, and it requires a lot of skill to design and implement. It is very difficult to maintain. And also these models are very oftentimes very hard to explain and debug and upgrade. If you have new data, if you have a new task to transfer, oftentimes you have to retrain the model to the list, or sometimes you need to redesign the model. And also it is very hard to repurpose to a different type of tasks. So that modelistic approach, is, as I indicated, limited. And people also sometimes prefer maybe another approach, as you see from Zhiting's example, which is built on, composition and also, maybe modularity. So now, when we build all these modules, to come up with a non-trivial solution, and again, we need to go into very intensive design and training phases, and maybe pre-train or integrate different components coming from different experiences. So do we still have, we need to still have maybe a substantial amount of knowledge to integrate them to solve the problem. So there is a lack of a coherent and compatible mathematical principle, to guide the design of this exercise, and also the algorithms may not be able to be reused. And as Zhiting just mentioned, when building real tasks, we often need to deal with a large amount of different experiences and data. And these experiences can be the data examples, It can be the prior knowledges coming from, say, knowledge graphs, or a set of rules. If you're lucky, you may be dealing with, or unlucky, you may be dealing with a real environment where your action coming out of a particular condition can receive a penalty or a reward. You may have the luxury of having a agent co-train with you and give you feedbacks in a positive and constructive way. You may also be unlucky to have an adversary which also want to beat you and therefore give you competitive experiences. And you also need to sometimes deal with a combination of all that. And as Zhiting mentioned, these days, each of these experiences and data pose a unique challenge. And typically what people do is to design a specific algorithm, to handle that. Reinforcement learning as a field is invented to deal with, environmental interaction and the rewards. Now, we see a lot of papers in the generative adversarial network training, which is to deal with the adversarial experiences. Now, how human being handles all these kind of problems? Obviously, we just have one brain, and we are typically not dealing with one experience at a time, right? We are very naturally combining all experiences, using a very integrative approaches. And how we achieve that? Do people have all these different modules in their brain encoded, one purposed for a particular type of information and do a particular type of inferences? Well, I don't know. But what we do know is that all these different functions are indeed integrated very well and coexist very well, and naturally can be very efficient. If you ask a machine learning engineer and a scientist to solve the same problem, even for a subset of the experiences, it is a very painful job. They are typically faced with a big zoo of a large number of models and solution and techniques. For example, those fan of deep learning people would probably dive into different type of neural networks, such as convolution network, LSTM, transformers, and nowadays there are bigger models like BERT, GPT-2 and 3 and so forth, right? To hopefully get a competitive advantage in performance. But there are also other engineers and researchers who may come from old school, and they want to provide maybe a very solid theoretical analysis and the guarantee of the behavior of the solution and the model. Then they tend to go to classical approaches such as boosting algorithms, PCAs, regressions, and so forth. And then in the middle, there is a big spectrum of techniques such as graphical models of all types, kernel machines of all kinds. So it really requires people to be very knowledgeable in this big spectrum, which is obviously very difficult in order to be creative and effective in producing solutions. Now you have a model, then you solve it, that brings you into another zoo of algorithm heuristics. Because in training this model based on different data, you have a lot of options. And typically, different options are again invented for unique type of experiences and unique type of models. For example, here we see names like reinforcement learning. It's a big field dealing with interactive experiences and rewards. We also see maximum likelihood estimation, which is built on static batch examples, sometimes streaming examples, and with a particular loss. So in a sense, you are really in a big maze of so many options of algorithms and the models and techniques. Therefore, the solution really depends very heavily on individuals' expertise and creativities. And what you can best hope for maybe is a bespoke solution that is specialized and crafted on a particular type of task. And of course, it is very skill intensive, and also it could be very, very costly and also time intensive. But what if you have many tasks that you have to deal with. What we see now in machine learning practice is almost like building runways that are only able to let a particular type of aircraft to take off. And if you have a new aircraft or new type, you need to build a runway. Imagine you want to build an airport that is capable enough to land and take off a wide spectrum of different aircrafts, and maybe also ready for new aircrafts designed in the future, to be able to use this airport. So what we're doing now in machine learning is not getting us, to such a perspective. All right. Okay, I want to pause here as a big kind of a brief introduction of the background, and then I want to maybe provide some thought about how we're going to approach a alternative solution to the challenge we have. I was a physics major when I was an undergraduate, and I love reading physics literature. And I noticed that in the early days of physics, such as in the middle of the 19th century, what the physicists see, in their world is not too much different from what I just described, in machine learning and AI. Just take the theory of electricity and magnetism as an example. There are, Gauss' law of magnetism. There are Coulomb's law of charge, Ampere's law of currents, Faraday's equations. So a lot of them, right? And then if you want to broaden a little bit and think about other phenomena like light, and there are particle theories, promoted by Newton, Laplace, and so forth. And there are also wave theory of light, by Huygens, Thomas, Young, and so forth. Not to mention that other people are studying the law of gravity. It's all very different if you just look at the literature. And the people at that point, regarded them as theories describing different phenomena. And therefore, in order to be fluent in physics, you have to learn a lot of all these case-specific paradigms and techniques and theories. So then there is this theoretical physicist, James Maxwell. He did something very, very interesting, right? What he did is to study all these equations, formulas, and theories related to electricity and magnetism. And he ended up realizing that he could just use a set of equations to summarize all of that. His set began with this 14 equations. This is still a lot, but it's already a good reduction of all the forms and equations available to them now. Then. And also one thing he did is very interesting. And he was also introducing very clean and unified notations so that originally seemingly different theory can be put next to each other and directly compared. And this is actually not trivial. Names like electrical fields, mathematical fields, are really already creating the first vehicle to reduction and then allow mathematical phenomena to be distilled and summarized. And this is even not happening in machine learning. Just take a simple example of, say, variational approximation of a posterior distribution in a arbitrary model, say a network model or a graphical model. At least I can come up with 6 or 5 names already, such as variational approximation, variational posterior, inference network, inference models, and encoders. So all these different names actually refer to the same thing, which is an approximation to the posterior, of a deep or multivariate distribution. And but the name, ambiguity and divergence are causing people to take them to be different. And therefore it is very hard to extract a common pattern out of it, not alone building connections between different theories, right? Such as, for example, the variational autoencoder and the GAN, they are different theories, how to make a connection between them two, right? So then what Maxwell did is to go through a further investigation of the symmetry between all different equations. For example, by introducing rotational symmetry, which really is about observing similar phenomenon in all different directions and represent the expression in vector form. He was able to reduce these 14 equations into only 4 equations. And then furthermore, with the introduction of more symmetry coming out of, say, special relativity and so forth, you are going to end up with only 2 equations, which can be unfolded and instantiated into each of these original form, that is for a special electromagnetic phenomenon in a particular direction, in a particular time frame. So this is beautiful. I think it really, really makes people free of the intimidation of understanding and mastering all the literature before you can understand the core concepts and begin operationalize it. For example, nowadays we operationalize electricity and mechanism in such a way that you don't need a PhD to wire a house. You can only have a high school phenomenon diploma, and you read a manual. You are pretty capable already, in doing a lot of non-trivial work to, be an electrician or, and so forth. So now we ask, in machine learning, is it possible to also have something like a standard equation, which can give a blueprint, of the major design and operations people need to engage in machine learning, such as coming up with the loss function, coming up with optimization solvers, and also plug in different model architectures. I consider these 3 to be the key ingredients of machine learning innovation and the solution building. But right now, there isn't really a very clean and simple blueprint for that. So our goal here is to suggest such a blueprint resulting from a unifying standard equation. So a good place to begin with presenting and describing the standard equation is perhaps the loss function, as the loss function is really the genesis of all ideas. It really leads people to design different paradigms and techniques to deal with different environments and handle different data, deriving the learning algorithms and validating the outcomes. So I'd like to suggest that it is possible to have a standard equation as a generic expression of the loss function that you will run into in all different learning paradigms. And at the very highest level, this loss function consists of the following 3 components. The first is called experience, and the second one is known as divergence, and the third one is called uncertainty. And I will give a detailed explanation of what each of the terms look like mathematically, and also how to design it and how to compute them. And this standard equation is defined as a function over 2 sets of random variables or random entity. One is theta, which represents the parameters of the model and also the structures of the model, and also a q, which is actually a function itself. It is a probabilistic function in most of the cases, which is actually serving as a variational form that is providing an auxiliary role in deriving the ultimate estimate of the theta. So let's use a few examples to see why this makes sense and how to appreciate from the first principle perspective. So we first look at perhaps the most classical algorithm in machine learning, known as the maximum likelihood estimation paradigm. We all know that in maximum likelihood estimation, you can work on a supervised learning problem where you use the likelihood function to describe an objective on fully labeled data, and then you can learn the parameters by maximizing the log likelihood of the function. And if your data is not fully labeled, then the likelihood function is a little bit more challenging to write down because now you need to marginalize over all the hidden variables inside this joint distribution, which is present inside a log function. And then you take expectation. This is algebraically pretty challenging to compute. And there is no closed form solution or expression of that. And then people come up with some heuristic. One of them is known as an EM algorithm, where in each step, you just impute those 8 hidden variables from some intermediate form, such as the estimate of the posterior of the hidden given the data. And then you plug in this imputed hidden variable so that this term become now fully observed. Then you go back to the maximum likelihood estimation. So this is a very well-known heuristic, although the genesis of that is a little bit mysterious. Right. Now let's take a different look into MLE using what is known as the entropy maximization principle. Okay, maximum entropy principle allow us to rewrite the MLE framework in a slightly more interesting way. In the maximum entropy framework, your loss function now becomes a Shannon entropy of the target distribution. And then you are going to learn this distribution by solving a now constraint optimization problem. And the constraint is written as the model expectation of certain features known as the sufficient statistics equal to the empirical value of the sufficient statistics. So we are basically using the data from the training examples as a constraint to basically control the final form of the P distribution to be learned. So this is a constraint optimization problem, which looks like a little bit more complicated than our original MLE form, but later you will see that it actually gives you a lot of flexibility in becoming more creative. So to solve this constraint optimization problem, you can use a Lagrangian method, and you basically could recover the analytic form of the joint in this exponential family distribution, taking this form. And then you can see that the final expression of the MLE estimate is the same as our previous page, even though they are derived from the maximum entropy principle. But this nice looking form isn't really offering you necessarily the end solution, because these theta are very rarely analyzable or computable in a closed form. You have to estimate theta very often using a fixed point iteration or other iterative methods such as gradient, stochastic gradient. One algorithm, which is known as the iterative proportional fitting, is actually a very, very general and convenient generic solution to solve the problem to estimation problem I just mentioned. And this algorithm is actually directly motivated by the maximum entropy formulation. In MLE, you can basically turn the original model estimation problem into a KL minimization problem, where you minimize the KL between the empirical distribution and the target distribution. And by minimizing this using a coordinate ascent algorithm, okay, each time you focus on one clique, or one component in the joint distribution and keep the other fixed, you actually come up with this algorithm in which the update of a particular clique function or a particular component function in the joint distribution is going to be computed by updating the previous estimation times the difference or the ratio between the empirical marginal versus the expected marginal out of your current estimation of the distribution. And when your potential function is parameterized, such as a local conditional distribution, or just exponentiated linear sum of features, as in CRF models, then this algorithm can be reduced to either a GIS algorithm or a stochastic gradient descent algorithm. So this algorithm is actually very general. Now, what if you have latent variables in your model, so that your MLE becomes a little bit more complicated in showing you a closed form target optimizer, you can actually still use a maximum entropy principle to write a much more easy to handle loss function. In here, we want to introduce a variational distribution Q of the hidden variable given the observation. This is also known as an auxiliary random distribution. And with that, you can express the log likelihood of partially observed data, as a lower bound that consists of a entropy term of the variational distribution plus a cross entropy between the variational versus the target distribution. And then this loss function turned out to be a lot more natural and straightforward to be optimized than directly solving this log marginal form. For example, the so-called EM algorithm can be actually understood in this very intuitive 2 steps. In the E step, you are actually solving a optimization problem in the Q space or in the variational distribution space where you minimize the differences between the variational distribution versus the target distribution. And then in the M step, you are going to now recompute the cross entropy term in the lower bound and then maximize it over the free parameter theta. So this idea of alternating between Q and theta, underlying EM, is actually quite a profound idea. It's like providing you an extra set of ladders in climbing a steep wall. Originally, you have just one ladder in climbing a steep wall of loss function. Now you have 2, and you are allowed to bounce back and forth between these 2 ladders or 2 auxiliary tools, to make the derivation or the expression of the update function in each step a lot more easier. In fact, this form and this form are a lot easier than directly taking gradient over this particular log of marginalized likelihood. And also, it gives you a vehicle or pathway to further simplify if you run into unexpected difficulties. For example, people find that when your target distribution or when your variational distribution are too complex, such as becoming a full network of multiple layers, then even computing the KL divergence between this tool can be difficult, and computing the cross entropy can also be very difficult. Then what's going to be happening is that you can now directly restrict the family of the Q distribution, of the variational distribution. People know, for example, the mean field algorithm or mean field approximation, that actually amounts to restricting the Q family into a fully factorizable product of simple components. And then there are other things like structured mean fields and Bethe approximations. They all amount to restricting the family of distributions of the variational approximation to a simpler one. And then basically your EM steps still goes as usual, except that now you are going to restrict the Q in a simpler space. And in the M step, everything is the same using the simplified Q. Okay, so this is very intuitive. Basically, I'm going to redefine this ladder to make it a little bit easier to climb. What if after this, you still cannot compute this? This is still too difficult because people notice that KL divergence between two distributions are asymmetric. Sometimes, changing the direction of the Q to P can make things easier. And that's actually an idea used by another well-known technique known as the weak sleep algorithm. The weak sleep algorithm invented by Hinton et al. Many years ago was actually recognizing that computing this KL term, okay, the original KL term between Q and P are too difficult, especially when this Q is, say, a very complex network. Then, in the approximation they introduced, which is known as the weak sleep relaxation, they're going to now reverse the direction of the KL divergence to make it from P to Q rather than from Q to P. And again, this is very intuitive, even visually. It's like now I'm going to make this two letter the same, but my projection function between the jumps become a little bit easier. And then that's still behind the EM step. And there are other tricks such as rate parameterization idea used in VEE, and you can also control the covariates and all that. These are all basically taking advantage of this very nice expression of the lower bound of the original, very challenging loss function by entropy terms, or cross entropy terms, resultant from the max entropy idea. So just to sum up, there is a deep connection between the MLE, the maximum likelihood estimation principle, and the maximum entropy principle. And by using the max n principle, you get a lot more clarity and also a lot more additional resource in simplifying existing learning algorithms, and which allow many techniques to arise more naturally as an approximation to the original solution. There is another type of learning framework which also connects very deeply to maximum entropy principle, which is Bayesian inference and also posterior regularization. We know that the Bayesian inference can be, there was a famous paper in the early 80s showing that a Bayes law can be actually expressed as a constraint optimization procedure where you minimize the KL divergence plus some cross entropy function between the posterior and the prior, subject to a constraint that the posterior is a natural distribution. Right? This posterior regularization idea is basically piggyback on top of that idea, which says that your constraint of the posterior distribution Q can be more stringent than just a natural distribution. For example, they could be made to satisfy certain sample-induced constraints. And there is a big body of papers originated, maybe the first one was coming from Tomi Yakala's group, and later on Junju et al. Also had a family collection of papers introducing different type of, say, max margin bounds, for predictive models, and also other type of bounds for latent variable models, such as LDA models and neural networks and all that. And the main idea still is the same. The loss function is a entropy term plus a cross entropy term defined by the variational approximation and also the target distribution, subject to that the variational distribution is going to enable a margin-based constraint. You can actually use the Longin method to solve symbolically the expression of the variational approximation in closed form, which looks like this. So this form is actually very intuitive. You see a very natural log linear additive effect of the current estimate of the model plus the features introduced by the constraints. In fact, in order to solve all these parameters inside this term, you will need to play with additional techniques, which I'm going to introduce a little bit later, that actually gives you opportunities to deal with nonlinear models, kernel effects, and other things. But I'm going to drive to the other direction, which I meant to quickly land, which is on the standard equation. So this technique, called posterior regularization, is actually not necessarily only useful for Bayesian inference. In a slightly more general setting, you could define a posterior distribution over arbitrary random variables that is not observed in the model. And you can treat the parameters either as random variable or as an unknown fixed constant, so that you don't have to be Bayesian to play with posterior regularization. But the equation, okay, of this estimation or machine learning framework remain the same. You have a loss function defined by an entropy of the variational term and a cross entropy of the variational versus the target, subject to some constraints. And in here, the constraints can be a lot more flexible. For example, a couple of years ago, one of our speakers, Zhiting, published a paper where he was able to introduce rules, first order rules, logical rules as constraints. Rules, of course, is not equivalent to data sample. they can be instantiated in many ways by different samples. Therefore, you can take expectation of all the different ways of instantiating that subject to the variational distribution of the sample, and then satisfy some constraints. And this allows you to bypass, in many cases, a data-hungry problem that language rules, linguistic rules, or sentiment rules, such as the negative sentiment after a but, do not have to be observed in the data because they are maybe not frequent enough to be observed. You can simply embed this rule into the model so that the resultant model can actually be smart enough to respect this type of bias. So up to, and this framework actually leads to a very generic EM style algorithm as a general solver, because now you need to estimate both the Q and also the unknown parameter theta. And this EM step shows you how to do it. In the E step, you estimate the Q using the form we saw before, which is a linear combination of the model plus the feature functions in the constraint. And in the M step, you maximize the cross entropy versus the unknown parameters to be estimated, right? In fact, you can even view the maximum likelihood estimation as an instance of the more generalized PR framework I just mentioned about. In here, all matters is to now replace these feature-based constraints with a different set of features. In the case of maximum likelihood estimation, your features are now indicator functions of the data points. If you see a data point, you put a delta function there. If you don't see that, you set it to be 0. And that alone will allow you to recover a maximum likelihood estimation paradigm that we saw in the earlier phase. Therefore, you don't need to have two sets of equations. This equation is adequate enough to cover both frameworks. So with this, you probably can see that there is an emergence of perhaps a general form of the loss function, which looks like this. Okay, we claim that in machine learning, many learning framework can be generically captured by the following standard equation of loss functions and optimization problems. The loss function can be expressed in two ways. One is a constraint optimization framework, where you see one term, which is known as the divergence between the variational approximation or the auxiliary function to the target distribution, and also the target distribution itself. The second term is an entropy term over the variational distribution or the auxiliary distribution. And then this function is subject to a constraint defined by features, which we will call them experiences shortly. That is, again, generic. Equivalently, you can express this constraint optimization problem into a grand Lagrangian, which is unconstrained, which contain a weighted sum of these three terms. And there are three parameters, alpha and beta, for you to control over. And there are also unknown quantities, theta and the Q, as the argument of the objective to be optimized. So now let me speak a few more words about each of the terms in here. The first one, E of expectation of the feature function with respect to the variational distribution is now referred to as an experience function. We saw already a few instances of the experiences in MLE and PR, which are, say, data examples and rules. And very soon, we will see that many other more advanced experiences can be symbolically, equally mechanically, embedded, into the same term in here. The second one is these experiences can be viewed as an exogenous regularizer to control basically the bias or the shape of the distribution to be learned. The second term is known as the divergence term. And here you can see there is a divergence defined on two distributions. One is the target and the other is the variational auxiliary. And this actually provides you a vehicle to start a very interesting learning dynamics. We can view the Q distribution as a teacher distribution, which in the iteration will keep assimilating the experiences into the updated form of its expression. And then by minimizing the divergence between the Q and the P, which is called a student distribution, you are making the student more and more like the teacher. And that's, in our opinion, a critical term to ensure that learning is leading to convergence and leading to optimum balance between the intrinsic model behavior and also the extrinsic exogenous behavior and the information. The last term is known as the uncertainty term, which controls the complexity, and the information, property of the teacher itself to avoid it become divergent or having, irregular behaviors. So this is a self-regularizing term, which is often taking the form of a Shannon entropy. Okay, so with this equation, let's take a look of, how, they can be utilized to solve our problems in hand. For example, let's begin by letting the standard equation to take on data experiences. Okay, we saw that before. The data experiences can be described by this feature function as a indicating function over data instances, and then the standard equation after plug in f function like this and the q as the posterior of the latent variable given the data, you recover a reduced form of this kind, which is actually what people recover in the standard maximum likelihood estimation under partial labeling. Now let's consider a more interesting data experience. Let's imagine that the data are not just given as a batch. Say the data come from some oracles that you have control over. You don't need to know the details of the oracle, but you have access to this oracle to get data from. And then you can also have a function that measures the informativeness of this particular instance data. For example, how much classification error it will generate, once you apply this data in a model and so forth. And then these two pieces of experience, one is the oracle source, the other is the uncertainty, can be actually used to form a new type of experiences, which we call the oracle data experiences. And let's see what happens if we plug in this experience back to the standard equation. We just plug this back into the standard equation and using that generic EM algorithm or the generalized EM algorithm to get to our updated equation, and they look like this. In the E step, we update the variational approximation using this, which turns out to be a log additive form of again the current estimate of the model plus the oracle features and plus the uncertainty features subject to normalizability. And then in the M step, you are going to now estimate the theta by maximizing the cross entropy, minimizing the cross entropy between the newly estimated Q versus the current form of the target model. It turns out that this equation is equivalent, to a paper, equation published in this paper in the Zhiting at 2007, which was designed for active learning. Okay, so basically, standard equation using the oracle data experiences allows you to perform active learning without changing any other components of the learning algorithm. You don't even need to know what is active learning, but you already are performing active learning. Another interesting area in machine learning is known as the reinforcement learning. And how about we take a look of what reinforcement learning look like in the lens of standard equation. So in reinforcement learning, you are not going to be dealing with the kind of data as we see in maximum likelihood learning or active learning. In here, we're dealing with states, which is denoted by X, and actions, which is now denoted by Y. And then in performing an action at a particular state, according to a conditional distribution of action given states, which is sometimes known as a policy, we're going to get a reward, which depends on your states and your action. And then you're going to be transitioning into the next state. Right? So the goal of reinforced learning is to use these dynamics, which is known as the Markov decision process, to allow learning the policy P of action given states. And a key ingredient in this learning paradigm is the reward function, which is defined as the cumulative rewards, from the onset of the game toward an infinite horizon. And your goal often is set to maximize this particular term, called the expected future rewards. And also, you usually assume the existence of a state distribution, which allows you to properly model, basically, the behavior of the state space. Now let's see, how about we let the standard equation to take on a new type of experiences coming from the rewards. For example, here we directly plug in the expected future rewards, as defined in the previous slides, into the feature function. And of course, our auxiliary distribution of the action and the states need to be rewritten in this form, where you have on the first part, the policy of action given states, and times the state distribution mu, okay, parameterized by the current value of the parameters. And your target is hopefully, the eventual, policy function you want to learn. So now let's plug all this, the feature function defined as the rewards, and the variational approximation and the target distribution all back into the standard equation in here. And suddenly this loss function becomes a form of this, okay, which has an entropy term over the auxiliary policy, the cross entropy of the auxiliary over the true policy distribution, and also the expectation, over the expected future rewards. And by the way, this term defines an upper bound of this term, which is what I call to be a reward excitement function. Basically indicates, it's basically the conditional probability of some action taking place such that the maximum rewards is attained and expected over all the distributions of actions and the states. Okay, so it turns out that this particular formulation is what is known before, in a couple of earlier papers where they were proposing RL as inference. Basically, they arrived at the same expression of the loss function as what we did here, and then subsequently they have a few algorithms solving this optimization problem. So in here, all we need to do is to plug in a reward experience and also make use of the state distribution available in the reinforcement setting and plug into the standard equation. And then we recover something that is known to be RL as inference. That's very interesting. And RL, of course, is a very big domain. There are many different ways, even on dealing with the same rewards. Just now, the reward was directly the expected, the sum of expected future rewards. But in another setup, the rewards was also treated in this way. For example, in here, we can use the logarithm of the expected cumulative rewards to be our feature. And then we plug in the Q and the P like what we did before. And suddenly, your new standard equation leads to the following EM algorithm. Okay, in the E step, you are going to now combine the current form of the policy with the rewards, the feature functions that is newly updated because it is parameterized by your new variables or coefficients in the policy. And then in the M step, you are going to now compute a derivative over the cross entropy, which actually turns out to be taking a form in fact, I'm not going to explain the details, but after, replacing, a analytical estimation of the expectation with a sample-based estimation, and after taking the log derivative tricks to exchange the ordering of the expectation and the derivative, you suddenly get a term in here, which is actually known to be the policy gradient algorithm, okay, in a number of very well celebrated papers. So you can see that the so-called policy gradient algorithm was nothing but an EM algorithm running on top of the standard equation using a particular type of reward experiences. Okay, so this is quite interesting. So we've seen a few examples of playing with different experiences. How about turn to another term in the standard equation, which is the divergence? How about we try some new divergence definitions? In the previous instantiations, this divergence is said to be the cross entropy between the Q and the P. How about in here, we try, say, a Jensen-Shannon divergence or KL divergence, okay? It turns out that once you replace the divergence function, you are opening the door to recover and enhance some of the techniques that is widely practiced in an area known as the generative adversarial learning, which I'm sure you all know and are excited about. For example, if you are going to set the divergence to be the Jensen-Shannon divergence, then your loss function is like this. And you just use the trivial data experience, like you see in the supervised MLE. The data experiences are just the expected indicator functions. Then, in your EM step, run against this standard equation, it turns out that in your M step, you need to minimize this Shannon divergence, Jensen-Shannon divergence instead of the cross entropy as we see before, with respect to the model parameter theta. And there are a couple of techniques to minimize this. One of the very interesting and promising technique recently emerged is known as the probabilistic functional descent, which I will be saying a few more words when we are getting into the algorithmic session. So basically, under PFD, you are going to now, instead of estimating this loss, you actually are going to turn your attention into another function known as the influence function. Okay, the influence function is obtained by solving, a conjugate dual, a convex dual of the original problem, like this. And then your optimization problem becomes now a minimax problem, because originally you are going to be, you need to minimize the theta. Okay, and now you basically replace the inner loop with another optimization problem on the dual, which is based on the influence function. And here you need to maximize over a new set of parameters, which are known as the conjugate parameters. And you have now the minimax problem. This one actually lies in the core idea behind this competing generative and distributive force in the GAN framework. In particular, if you are going to set the conjugate function phi to be taking a particular form like this, okay, and the C function can be an arbitrary neural network parameterized by a new set of parameters pi, then you will be recovering exactly the vanilla GAN training, okay, where you are alternating between learning the discriminative parameters phi and also learning the generative parameters theta, okay, to achieve a game theoretic equilibrium at the end. But the SE function is allowing you to do more than that. It allows you to do more than just choosing a different divergence function, but also you can additionally choose different adversarial experiences. If you do nothing, you basically get the experience to be just the sample experiences as we see in MLE. But now you can also parameterize your experience function. For example, what about making the experience into a binary classifier of the generated samples being choose or from the artificial, being real or artificial, right? So that being from the generative model or from the real data. So that's a parameterized experiences, which allows you to, simply plug in and then at the same time introduce the discriminative parameters. In fact, you can, really exploit the vast space of designing adversarial experiences. If your experience is just a binary classifier, you actually will be recovering the vanilla GAN. In here, your vanilla GAN is a little bit easier to recover than using the probabilistic functional descent, because there you need to introduce a function to the complement of the original function. But in here, you directly plug in the discrete network as a experience function in the original plane SE equation. That is actually a lot more easier. And then you can also try fancier discrete functions, such as, for example, a multi-class classifier, for example, or you can make it a one Lipschitz function. You can also further change the divergence function to be a F divergence. So with all this and this in combination, you can recover a number of very well-known variations of the GAN model, such as the F GAN and the W GAN and so forth. So I'm not going to go on and on because that would take quite long, but just to sum up, there are many algorithms that can be recovered by the standard equation. Here is just a tree of all these algorithms showing you such connection. And this is a table showing you where each of the term look like in all these different incarnations. But of course, recovering such a known algorithm or framework is not the goal, not the only virtue of the standard equation. Right? The standard equation is really giving you a space to do arbitrary creative design of the experience, of the divergence, and of the uncertainty, so that you may eventually end up with a learning paradigm that you don't recognize in the current literature. That is something what we want to see at some point. Someone may ask, is the standard equation covering all what we know already? Well, not quite. We haven't really got time, or there may be a limitation that we don't see yet in the standard equation in describing current algorithms. For example, we haven't figured out how to really use the SE to describe this very big space of a meta learning framework, where you are trying to learn how to learn. You are trying to learn something that is transferable further on with a subsequent task and so forth. There hasn't been a systematic examination of how to apply SE there yet. Lifelong learning is another area that is very interesting, which we want to look into, but we haven't yet. Right? So I think it's very interesting to do a number of future work to study basically these connections down the road. So before I jump into the algorithmic part of how to solve the standard equation, I just want to wrap up by reminding you that with the standard equation, one obvious free outcome is that you see all experiences already coming together. This is echoing the title of this tutorial, that you want to learn with all experiences. In here, your experience function really gives you a very straightforward vehicle of making weighted combinations, okay, of all different experiences. In fact, we even have reason to believe that through the potential offered by the standard equation, you may be able to pursue nonlinear combinations or kernel combinations of different features to really get complex interactive effects. That's a direction that we haven't studied, but I believe it's very interesting. But with the standard equation, it allows you to really focus on what to use rather than how to use, because there are some big hammers in the algorithmic space, such as the generalized EM algorithm as described, which allows you to really solve hopefully novel standard equation without reinventing or reinventing new algorithms. But now let's look into the algorithmic space a little bit more carefully. The zoo of algorithm, the operand solvers is really big. As you can see, there are all different algorithms invented in a very, very a use case specific fashion. For example, proximal policy optimization is an algorithm that is known in reinforcement learning, right? And it is, of course, less well known, in, for example, maximum likelihood learning or in gun learning. And there are other specialized algorithms, such as the kernel trick, that is used in posterior regularization, but it has never been used in other places. Right? So we ask, are we lucky enough, to be like having a standard equation for the loss? Is there a master solver to optimize such a standard loss? Unfortunately, so far we haven't seen such a thing yet. I guess there are a few techniques which are promising to be quite general. For example, this alternating gradient descent is very widely used. We already see that EM algorithm, variational EM algorithm, weekend sleep algorithm are just instantiations of this very general gradient descent, alternate gradient descent idea. It looks like this, right? In the E step or in the what we call the generalized E step, you are going to update the auxiliary equation or maybe the variational approximation to the target. And this update actually takes an interesting form, which allows you to combine current model with new experiences. Okay. And then in the M step, in the generalized M step, you are going to, in this case, minimize a cross entropy between the Q and the P to get the optimum estimator of the theta. These two steps are really like a teaching and a student algorithm, as I see. And I think this is a nice analogy to highlight the fact that you are going to do the acquisition of the knowledge and also the update of the model in two alternating steps until they converge. And under this inspiration and intuition, there are many small or large or sometimes very creative tricks and heuristics invented in all this direction, which I don't have time to cover, but you can see some of these names already mentioned, PPO, max M reverse ERL and all that. They are originally invented in different learning paradigm, but now they can be seen as a generic tool for the standard equation. But unfortunately, the standard, the generalized EM algorithm does have limitation. For example, you cannot apply this algorithm to a case where the divergence is no longer the cross entropy. Say it is a Jensen-Shannon divergence, for example, or other more complex divergence measure like F divergence. This algorithm doesn't seem to be working. So let's look at a few advanced techniques recently emerged that can address some of these issues. Here I highlight a few key ideas that I find to be both very interesting and also have the potential to be having general benefits. One is the Lagrangian duality trick people use to introduce the kernel technique. And the other is what I just mentioned earlier, the probabilistic functional descent. So let's look at first, the duality trick. So in the literature of posterior regularization, people realize that by expressing, the margin constraint, in this framework like this, then, in the generalized EM step, you are going to get a symbolic expression of the posterior in every step, look like this, where you see a combination of the current estimate plus a linear combination of the margins. Okay, so this is a very, very important insight because you can now because these are linear combinations weighted by the lambda, which are the Lagrangian multipliers. And when you solve this lambda using a Lagrangian methods, you actually could expose some very interesting algebraic phenomena, such as the KKT condition, the complementary slackness condition, for example, to actually expose, to reveal that only a few of the samples known as the support vectors are corresponding to non-zero estimation of the lambda. So this is actually one of the key insights, exposed due to the technique of duality, applied to the original primal problem. And additionally, when you solve the dual problem, you run into this very interesting expression, which exposes a quadratic form of the weighted sum of the margins. And this quadratic form actually now allows features to be only interacting with each other in dot product form. Therefore, you can just replace the dot product, with a kernel function, and therefore automatically you can allow the kernel trick, to give rise to nonlinear interactions between experiences. So look, this technique was originally only applied to the posterior regularization, where you have only one type of experience, which is the sample-induced margin experiences, max margin experiences. I suspect that when we now apply linear combinations of all different type of experiences, you may still use the Lagrangian, using the convex duality trick to visualize the problem or analyze the problem in the dual space, where the sparsity effects and the support vector effects and also the kernel effects may actually be also available, for experiences of different type. So that's actually an interesting area that I'm very, very curious to see down the road. Another generic technique that can be also very influential down the road is coming out of the recent paper published by Chu et al. Really advocating this technique known as probabilistic functional descent. This is actually a very classical technique, in probabilistic functional estimation. Basically, it allows you to turn the original, estimation problem of a probabilistic of functionals, okay, in a probabilistic functional space, into something that is simpler. We all know that solving estimation problem in a space of functions is a lot harder than solving them in a space of parameters, right? So therefore, the PFD technique allows you to, expand this functional, like what we did in Taylor expansion, over a particular anchor point of the function, okay? And that anchor point, in fact, can be described by, a function called influence function. So you get the differential of this original functional loss, using the Gateau differential technique. And then you are required to obtain a expression of the influence function, which is defined like this. And the influence function can be actually, once you have that, then you can now approximate the original probability functional as the expectation over a function and the plus some constant. Therefore, you effectively turn the original functional optimization problem into a parameter optimization problem, using the influence function. This is a very neat technique. And now introducing, for example, a particular form of the functional, such as say a Jensen-Shannon divergence between two distributions. Then, you can now write down the convex dual of the original, hopefully in a closed form. And then you can solve the influence function by solving this dual problem, okay? And in here, if you are making the choice of letting the complement function of the original loss to be taking the form of a discriminative network, for example, like this, then suddenly your influence function will take the form of this, okay, which is actually helping you to recover the discriminative the discriminative function people usually want to implement or design in the generative adversarial network learning framework. So then by plugging back into the original optimization problem, you actually have a minimax problem where in the inner loop, you are going to maximize over the discriminative parameters, okay, to optimize the discriminator. And then in the outer loop, you are going to optimize over the generative parameters to optimize the generator functions. Right? That basically recovers you the GAN framework. So this algorithm is pretty neat that you don't have to basically, mechanically, plug in, a generative framework and a discriminative framework, and your loss function plus, a driver algorithm automatically gives you that, adversarial dynamics between the generator and the discriminator. Similarly, you can apply the PFD to a different type of standard equation loss, where the experience function is now set to, say, the cumulative rewards, in the reinforcement setting. And by running the PFD, suddenly you can also recover an expression which gives back you the policy gradient algorithm. So it's actually also recovering a number of well-known algorithms in different learning paradigms. So there is a potential that PFD, just like the alternating gradient descent, can become a pretty general driver over a large spectrum of loss described by the standard equation. And here I just give you a few examples, either published by the papers or by us that recovers some of the well-known algorithms using PFD. Last but not least, of course, in the whole endeavor toward a blueprint of machine learning, you need to worry about also the blueprint of a model architecture. This is a very interesting space. In my opinion, is best served by the current research community. There are a lot of innovations and ideas, even standardizations and catalogs available now, for designing neural networks, for designing graphic models, or even compositional architectures, which allow us to really, define very nicely the space of a Q and a theta, in a highly compositional manner. But I'm going to leave it to the next part, where when Zhiting is going to talk about the tooling, he will be showing you a lot of examples, of model architectures, for under the machine learning blueprint. So to sum up, we now have a blueprint of machine learning instantiated or maybe defined by the standard equation of the loss, which consists of an experience term, a divergence term, and a uncertainty term. Right? And we see potentials of a few driver algorithms. Each can be used to mechanically derive a number of powerful algorithms that is already in action, originally invented by different innovators and researchers in different domains, but now they become, a tool available for solving the general equation, the standard equation. Next, I'm going to maybe give you a few examples of how to make use of this equation, the standard equation, to make life easier, or to maybe exploit more capabilities and functions without reinventing the wheel, before I hand it to Zhiting to provide the actual interface and tools to make those happen. So why this is useful? I guess what I was trying to present just now isn't just for the purpose of showing a beauty, in the unification. In physics, there's always this desire to express the universe and the whole knowledge using as few expressions as possible. Of course, here we would enjoy having that simplicity and the clarity and modularity. But beyond that, what's more important is that it actually exposes a lot of utilities that we didn't realize before. And also it could make the realization of these utilities a lot easier and straightforward. For example, I already mentioned there is an opportunity now to learn with all experiences just by defining the experience function as a sum of all experiences. And that actually will give you chances to broaden the use of originally specialized algorithms. It's like making your runway now ready for different aircrafts rather than only the runway for reinforcement learning aircrafts. Right? And also it allows you to do very flexible experience composition and the different combinations. I just mentioned that this mathematical framework opens the potential of complex interactions between experiences, such as nonlinear interactions, such as maybe infinitely higher order interactions, due to the kernel effects. And in fact, I think even from a pragmatic point of view, having a standard equation is probably indispensable when you want to design a new generation of AI agents, which is going to be trained and deployed in a more realistic game theoretic learning framework. So our current learning, machine learning, in most cases, is really agent-based, and in fact isolated agent-based. When you are developing a recommendation system to a client, you don't assume that the client is actually also having access to 3 other recommenders, and you actually need to compete with the others. If you are driving a car, it's not like you receive signals. You may want to also either send signals or receive signals from other cars on the street or in the city. So that actually will influence your perception of the world and also your decisions and your value and so forth. But you can see this game theoretic setting where you have multiple interacting agents requires you to be able to handle multiple experiences, both as a raw data sample, such as image and text, but also rewards, uncertainty, and adversaries and others. So this standard equation makes you ready to embrace and integrate all these experiences, because the mathematical framework is naturally designed to fit that kind of needs. None of the existing framework gives you that flexibility of designing these agents. I believe this might be, again, a very, very rewarding experiment and future direction, to really open up new opportunities for machine learning. All right, let me wrap up very quickly with just a few examples, which are kind of technical, but with the standard equations mathematical picture, which allow them to be more easily understood and also hopefully more easily implemented. So learning with all experiences begin with repurposing all different algorithms, because in the past we usually are in the world of one algorithm, one experience, that kind of a mapping, right? And you don't basically use, for example, a policy gradient algorithm to learn, sample-based kind of maximum likelihood kind of problems and so forth, right? But let's see a few examples where some new needs and some new opportunities may actually call for this kind of innovation. For example, in our posterior regularization framework, we said that we can introduce logical rules to be the set of knowledge-based constraints, okay? And there are many, many rules. Some are maybe more powerful, some are more useful, some are less, some may be a wrong set of rules. So how can you actually basically assign weights of different rules? Right? I don't think it is very well studied, in the posterior regularization framework yet. But let's see, how this problem can connect to what is known as the policy gradient algorithm and maybe RLS inference problem or reverse RL problem that is well studied in the reinforcement framework, where learning policy or learning rewards is actually one of the new frontier, in innovation. So here is example. In the framework of max and inverse reinforcement learning, the rewards are parameterized. Okay, they basically allows the agent to learn the validity and the soundness or the value of the rewards, using a formula which is running in a EM mode, where in the E step you are going to update a policy function based on the newly weighted rewards. And then in the M step, we are going to solve this cross entropy optimization problem, by relearning the weights of the rewards. So this algorithm is well developed, first of all, originally by Zibard, and then by many other authors, known as the Maxwell inverse RL. Now let's look at the problem in PR, in posterior regularization with the learnable rules. It's almost symbolically or morphologically the same, that you can write down your rules using a parameterized form, okay, where each rule is giving a weight phi. And then symbolically, they look the same as the parameterized rewards in the reinforced learning. And in fact, under the standard equation, there are no difference between RL and PR, and even though one is called rewards, the other is called weighted rules. And therefore, the same algorithm that people invented for the max and inverse reinforced learning can be directly deployed on the standard equation to learn the weights of the rule without basically any fuss and reinvention. Okay, so that's kind of a very, very good benefit of repurposing an algorithm. Let's look at another example where, say, we do supervised MLE and maximum likelihood learning, where we are given samples. What if the samples are either too sparse or not fully reliable? Are you interested in, for example, imputing more samples based on a given sample, or reweighting the samples, or augment those samples? Well, there isn't really an algorithm in the MLE framework for doing so. But again, in the reinforcement learning field, reinforcement learning is a very, very fertile field where many great ideas has been invented, because learning with agents in an interactive environment is always challenging and kind of push the limit for many new inference algorithms. So let's look at this algorithm known as the intrinsic reward learning. So in this setting, the rewards broke down into two parts. One is known as the extrinsic experiences or extrinsic rewards, which is invariant, which basically is attributed to any experiences that an agent could experience regardless. And the other part is a intrinsic experience, which is parameterized. Basically, that reward really depends on what kind of experiences and what kind of states you are in, and it will be changing. So the joint rewards has an invariant part and has a variable part. And look at our augmented MLE scenario. It's actually similar. In the augmented MLE rather than the original MLE, you want to treat the data in a slightly creative fashion. You may want to treat some data points, as it is. Okay, they are basically either present or absent. Therefore, they don't need to have a sample-specific weights. But there may be some other data points or your imaginative or imputed samples to bear a weight. Therefore, their importance and the value can be augmented. Right. So in the intrinsic reward learning setting, you can plug in these reward experiences and back into a loss function, which again can be expressed as an instance of the standard equation. And then algorithms has been invented, to solve that. And in this case, we can pretty much just use the same trick of intrinsic plus extrinsic rewards for the data to augment them, so that every data points gets these two components, and then you plug in this intrinsic reward learning algorithm, into the standard equation. And now you are no longer doing MLE. You are doing literally, MLE with a data augmentation without now defining or reinventing a new algorithm for that purpose. One last example I want to share, which I thought is also quite insightful and interesting, is for a different purpose. This is for improving algorithm quality rather than just enable a new type of learning capability. In here, say in gun learning, for example, it is well known that GAN models are very hard to train. There is a delicate balance and interplay between the generator and the discriminator. And once your updates are making too big a step, you may tip off and cause a divergence, or just get a very weird answer, right? So this stability issue in GAN training has always been a challenge for many practitioners, especially. And again, stability question is studied in depth in the reinforcement learning world. So let's see how we can use some of the ideas there to treat a stability problem. For example, in reinforcement learning, there is a algorithm known as the proximal policy optimization, where the proximal term is to kind of augment or smooth, redefine the original loss function that is ill behaving with a smoother, nicer behaving approximation. And then you're going to run P policy gradient and other optimization on that. Right? So how about we apply the same trick to the GAN training? You can see a contrast. In the conventional GAN model, you can see this very, very, scary divergence once you are changing the interpretation step. Basically, almost like the learning rates or the learning magnitude of the model. And it looks like if you are not careful and step out of a certain size limit, your objective will be divergent. Okay. But using a PPO, you can see that there is a kind of a saturation point where if your step are getting too big, you are kind of into a trap, and then you actually wouldn't get as nice an objective. Therefore, you will be pulled back to stay with the size. Right. So that basically provides you a very, very natural stability mechanism to prevent the learning step to go too large to crash the algorithm. In another example, similarly, there is an idea used in variational inferences, where people use importance weighting, to again augment, the effect of every training instances. And likewise, we can use this same algorithm for the standard equation now defined, to capture the GAN phenomenon or effects. And you can see it is indeed stabilizing in both the case of the discriminative loss and the generative loss, the behavior of the algorithm. You can see that the magnitude of the variation is either dramatically reduced or at least meaningfully reduced from the original algorithm that is using the intrinsic or the original algorithm developed in the GAN community. So I'm going to wrap up now. There is, as I mentioned, a huge space of exploiting, the promise of learning with all experiences, such as using the repurposable algorithm to solve problems where experiences gets rich composition. And here I just give you a highlight of how this composition could look like, right? Imagine you train a conversation system or a chatbot where you want the chatbot to behave like a human in terms of they speak the right language, linguistically correct, but also they should understand the right sentiment of the conversation. They should also follow certain linguistic rules and all that. Again, training such a model may be very expensive. Of course, you can say maybe the BERT model and the GPT model could overcome that. But even so, sometimes a flexible retrainable and repositionable implementation can be valuable. And in this case, the standard equation allows you to really combine experiences coming out of a sentiment classifier, out of linguistic rules, out of language models in the combo, and then very quickly produce a trained system that achieve a compounded effect of all these behaviors. Okay, so I come down to the conclusion. In sum, the standard equation is meant to provide a blueprint that allow people to learn under different type of experiences, and also using different loss functions to qualify and to guide the training and the teaching and the student effects. And it really allow people to repurpose many of the existing algorithms and recover many of the existing technique for their reuse and redeployment. But also it opens the way to hopefully come up with new solutions and new algorithms. So with that, I'm going to stop, and I have time for a few questions before the break. Thank you.
Thanks, Eric, for the first part of this tutorial. Yeah, so yeah, if you have any questions, please feel free to post the questions in the chat box. And now we see some questions already. Let me take a look. Yeah, so one of the questions is, yeah, can you help to illustrate an example on how to leverage the experiences from a knowledge graph into the standard equation?
Thank you. That's a very interesting question. Maybe Zhiting will do more in his part, but you can imagine a knowledge graph. What is a knowledge graph? Symbolically, you can express knowledge graph, the path on that, or the neighborhood connectivity of that as a collection of first order logic rules or constraints, right? So that's basically how you reduce the graph into clauses and the rules that could be expressed into into the standard equation. That's how I would do that. But of course, practically it is very challenging, because if you want to encode every piece of knowledge and constraints on knowledge graph, that's a huge space. It's a graph space of all possible connectivities. Whether you want to do that, it's basically a trade-off between the resource and also the necessity. I can imagine maybe a different way of redesigning a constraint. Maybe Zhiting can chime in, where you do a reverse check. You basically see a data example or a piece of conclusion. You map back into the knowledge graph and see whether they are consistent or not. So it's more like a consistent a constraint, rather than a predefined set of rules in the standard equation. How algebraically this is to be implemented, I will leave Zhiting to answer those.
Yeah, so yeah, as Eric mentioned, the standard equation basically provides you a interface to design this solution to say integrate the knowledge graph in learning process. And this interface basically reduces this problem into this kind of consistency check, right? Say you have a sample from your model, and what you need to do is to design a consistency kind of function to measure, okay, how well this sample is aligned with your prior knowledge, which can be a knowledge graph, which can be a logical rules, or whatever other even more non-trivial and complex experiences, maybe another model, basically. So in the second part, we will give a very concrete example on how the standard equation enables us to incorporate these different type of experiences to in a kind of a new learning problem. Yeah. Okay, so yeah, next question I've kind of answered a little bit in the chat box. Basically, can you provide a link to a paper that surveys all these applications of standard equation?
Yeah, so at the end of this deck, we have 2 pages of references that gives you some examples of the application, and also some fragments of the mathematical formulation. The standard equation itself hasn't been published as a paper yet, but it is in the formation. So yeah, we will be posting our slides, on the website, so you can download it.
Yeah, so I think it's okay. So a new question. Can you comment on neural differential equations and how standard equation helps unify things?
Comment on neural differential equations?
Yeah, it's kind of like in the neural differential equations.
So yeah, so now you can see we're running into the problem of a terminology thing, right? It looks like a new terminology. I think I know it. It's like replacing the original maybe simple gate function or activation function that is associated with the edge into some say continuous time equations, or some other more complex differential equations. Is that what ODE stands for, or the neural differential equation stands for? In that case, it's pretty natural into the standard equation. Remember that I leave out the architecture, the model architecture part as a standalone module, because the standard equation is talking about the loss, about your optimization target. And in the loss function, you can plug in different formations of the Q and the theta, and your neural differential equation is a particular choice for the form of the theta or the form of the Q. Therefore, it actually becomes already modular. So in the second part, you will see how different modules can plug into each other and create hopefully a novel combination, but without reinventing, in fact, the algorithm, because the same, backprop and other algorithms which originally already work for each of the modules can be just directly, incorporated as a subroutine in our generalized EM algorithm.
Okay, cool. So probably another question posted a little bit earlier. Has new libraries been developed that utilize this standard equation interpretation of machine learning?
I would say yes and no. We just started to, come to a realization that this standard equation has the great potential to unify and to even instantiate new learning paradigms. Text, for example, is one of the toolboxes developed by Zhiting and his colleagues and the members of the company. We are in the process of making it richer and more accessible.
Yeah, so yeah, we will be talking about Texer and this kind of libraries in the second part, and all the resources, like the links to the GitHub repo and the tech reports will be included in the slide. Okay, so it looks we don't have other questions so far.
Okay, then why don't we have a break? The baton is back to Zhiting, so you can determine the cadence for the rest of the talk.
Yeah, so we can have a 10 minute, around 10 minutes break. I guess we can come back on maybe at, let me see, 3:05, I guess. Okay. Yeah, let me share this schedule for next step. Okay, cool.
All right, thank you for your attention. We'll see you in 10 minutes.
Okay. Yeah, I guess we can probably start the second part. Okay. Yeah. Thanks everyone for coming back. Yeah. So in this second part, I will be talking about tooling for operationalizing the framework of the standard equation and enabling learning with all experiences, and especially enabling easy composition of machine learning solutions to solve problems with different type of experiences. So before diving into the topic, let's first do a quick recap of first part. Yeah, so we have been discussing the standard equation, which is in this form, which consists of basically three terms. The experience term, which encodes the different type of experiences in a uniform format, basically, through the F function. So the experiences can be like data examples, rules, rewards, and adversarial models, and many others. And the second term is the divergence. Basically measures the distance between the auxiliary distribution Q and the model of interest P set. By minimizing this divergence, we encourage the model to stay close with its teacher Q, so that the model can basically inherit the information from the experience. So the divergence can also take different forms like cross entropy, Jason-Shannon divergence, F divergence, Waterston distance. And the third term is uncertainty, basically providing a self-regularization of the whole system. And yeah, so in a higher level, right, the three terms in the standard equation basically defines the loss function of the learning problem. And we minimize the loss function with the optimization solver as discussed in the first part. And note that the experience is one of the key ingredients in the loss function, as we highlight here in red. And the third, which denotes the model of interest, in particular the model architecture, is another key component defining the whole learning problem. And at the end of the day, we want to learn the model to get the estimation of the model parameters so that this model can be deployed to solve the problem. So we'll be discussing more of the model architectures in this part. Yeah, so in this part, we'll be moving a step further from the theory of standard equation to operationalizing this framework. And I will basically discussing two parts. The first two sections. The first section is about machine learning solution design. We show that through concrete examples that with the standard equation, we can design machine learning solutions by simply plugging upstream experiences available in the problem to drive the learning. And in the second part, we will see the tooling that enables composable machine learning, so that we can use these tools to easily assemble solutions. Okay, so yeah, in both of these sections, I will provide very concrete examples so that we can go through the running examples and get the idea of the operationalization. So in the first section, problem solution design. So the high-level idea is pretty straightforward, as Eric mentioned in the first part, with the unifying formulation, which basically says that distinct experiences can be used in learning in exactly the same way, which is captured by this experience function F. Now we could just plug whatever available experiences into the same learning procedure, right? Specifically, here F can be, the F function can be set to whatever experiences, as long as the experiences are written in the form of an experience function. And further, this F can naturally be set to a combination of different type of experiences. Yeah, so this basically offers a new interface to design problem solutions. Say for a data scientist or domain experts, they can focus on what experiences to use based on the problem itself by designing the F function. And we don't really have to worry too much about like how to use, because the single integrated algorithm can basically just handle all type of experiences in the uniform way. So next, let me demonstrate how this approach could be used to solve a concrete problem. The problem we'll be using as an example today is called controllable text generation. In particular, we'll take the example of controlling text sentiment. So the problem is like this. We are given a source text, say a sentence, the manager is a horrible person. And additionally, we are giving a targeted sentiment like positive. So the goal of the problem is to rewrite the original sentence and generate a new sentence that has the targeted sentiment, while preserving all other aspects like the contents, the entities, the subjects, or other different aspects. So in this particular example, the desired output will be something like the manager is a perfect person. So this kind of problem is very useful in many application scenarios, such as building emotional chatbots, and like say creating adversarial examples in text, and also like if we go beyond the controlling sentiments, we say we want to control other attributes, then those kind of techniques can be used, like say neutralizing biased text on social media, and so on and so forth. So the key challenge of this kind of problem is that usually there is no direct sufficient data. So that which means we cannot just train a generation model supervisedly in an end-to-end manner. Yeah, so to design the solution for learning in such a problem, as the integrated algorithm or the standard equation tells us, we can focus on what experiences to use based on the problem structure. So yeah, so we take a look at the goal of the problem, right? So in this problem, we see that we want to teach the model about the concept of sentiment, right? Because we want the generation model to control the sentiments of the text. Then a natural form of experience that encodes this concept is for naturally a sentiment classifier, like a pre-trained sentiment classifier. So given a sentence, the sentiment classifier evaluates the logic of the targeted sentiment. Right? Basically, it measures how well this input sentence is aligned with the targeted sentiment. So this is the first type of experience we can use as part of the F function. And next, as another part of the problem goes, we want the model to learn to preserve all other aspects of the input sentence, such as the contents, the entities, or the things. So to achieve this goal, a sort of surprisingly simple type of experience that we could use is a weak form of data examples, which is just like self-construction data. Like in this case, given this text of negative sentiments, we intentionally set the targeted sentiment to negative, the same as the input sentence. So given the problem definition, right, the ground truth output will be exactly the same as the source sentence. The manager is a horrible person. So this kind of like automatically constructed auto-encoding data or self-constructing data can serve as a type of experience, a weak form of data example, to encourage the model to preserve the input aspect. And then if we analyze the problem further, the basic requirement of the problem is that we want to generate a new sentence. So of course, we want the sentence to be like high quality, fluent, and grammatical, right? So then we imagine like we can think what type of experience already encodes this kind of like a fluency of language, right? So to give the model this kind of information, a natural form of experience is then a language model, right? A pre-trained language model. Given a generated sentence, a language model computes the perplexity score, assessing the quality of the sentence in terms of like fluency and the quality of the sentence. So this language model serves as another part of the F function, the kind of the score function. And there can be other forms of experiences that can be helpful, but here I will omit due to time limits. So once we have identified these many types of experiences, the next step is to like plug them into the algorithm and perform learning on the model. So here's a very interesting case study where we plug in the experiences one by one and see what the model really learns from the experience. So the input sentence again is the sentence, the manager is a horrible person. And if we only plug in the sentiment classifier as the F function and you train the model using this by minimizing the loss function defined by the standard equation, the resulting output by the learned model on this particular case is like good. So we see that the model does learn the concept of sentiment, right? Because good is a sentiment, is a token of positive sentiment. But of course, this is not the correct language, right? So next, we plug in the second type of experience, the self-construction data example, to encourage the model to preserve the input aspect. Then we see the output. The manager is a delicious person. So we see that, okay, this model does learns more, right? Learn more because the sentence, like the manager is a delicious person, kind of like preserve more aspects of the inputs, like the manager, right? The subject is the same, person or anything, right? So the entities are preserved. But again, this is not what we want at the end because this is simply not a correct language. So we plug in the third type of experience, language model, to give the information about what a correct language is, and we end up with the correct result. Like the manager is a perfect person. Right. So this is a case, pretty simple case, showing that with sufficient type of experiences, we can learn the model as we want without within the unifying framework. And without using any like direct supervision data. And here are more quantitative results showing that with these more and more experiences, the model satisfies different evaluation metrics of the problem, like the accuracy of the sentiment and the preservation of different aspects and the quality of the language. Yeah, so the same method, the same methodology for problem solution design were applied to other controllable text generation problems and made rich results. Say besides controlling the sentiment, people also enable learning to rewrite the content of sports commentary, given the new kind of box score table, so that we can automatically generate a sports report. And similarly, one can build conversational agents that can proactively guide the conversation towards any specified topic. This can be useful for building a conversational recommender system. So in all of these problems, we don't have any direct supervision data, but rather we use other various forms of experiences, like language models, like logical rules to evaluate the closeness of the current conversation topic to the target topic, and the kind of content fidelity of the generated text with the input box score. So this unified framework basically gives you the interface that you can just plug in all these type of experiences into the learning process. So another instance is image generation in the fashion domain, such as in a virtual clothing try-on system, in which we generated images of a person under different poses. And here we integrate constraints about human gesture to ensure the system would generate meaningful fashion images. I won't dive into more details here, but just show some results. So the input on the left hand with we have the input to the model, which is the source image of a person, and then a target pose encoded as the skeleton of the human body. And on the right hand side is the true target, the ground truth. Basically, we want to generate an image of the same person, but under the target pose. And with like base model, like say a generative adversarial network GAN with supervised learning, basically this base model does not use any like structural knowledge or constraints. We end up with this kind of results where you can't really see very clear or meaningful human gestures or like a human body configuration. And after applying this constraint of human gestures, we get much better results where you can see this human body structure, which are pretty close to that of the ground truth. Okay, so the framework based on the standard equation really provides us with this turnkey mechanism to design algorithmic solutions to deal with all types of experiences. One could compose the available experiences and plug into the framework to drive the learning. And indeed, more generally, such compositionality of machine learning is the key vehicle to get to our goal of learning with all experiences, to be able to quickly assemble a solution in different problems and with different available experiences, and in a very systematic, reusable, and repeatable manner. So this is different from the one-off design or implementation. Here, the solutions are built like playing Lego or like composing music with basic music notes. So next, I'm going to introduce more details of such composable machine learning and how it really helps with solution creation. Again, I will demonstrate with concrete examples to illustrate this concept. So due to the time constraints, we will use a much simpler problem compared to the controllable text generation problem as we just saw in the first section. So here the running example is machine translation, where we want to translate text from one language to another language. And we will see even such a much simpler problem can involve very different, quite a few components, including handling data and experiences. Here, the experiences can be data instances, right, as we commonly do in practice, these language peers, basically. And additionally, we can have other type of experiences, like the reward metric that measures how well the generated text is aligned with the Lagrange's text, translated text by human, basically, through some like structural magic, like BLEU, like other like semantic scores. Or we can use adversaries, like how like GAN models are used in image generation. So we have different type of experiences that can be used to this problem. And then we build like models, like the model architecture, which again can be of different choices, like recurrent networks, like transformers, self-attentions, and many others, as we'll see more examples later. And then with this experience and this model, we can specify the loss function, right? Probably under the standard equation framework. Yeah, and we run the training, right, based on different criteria and different needs. Yeah, so this is the example we will be using. And to build a solution for such a well-defined, relatively simple problem from scratch can already easily go beyond the tens of thousands of lines of code to implement the whole pipeline. So let alone the subsequent efforts such as like debugging, tuning, maintenance, upgrading, and so on and so forth, right? So here, composable machine learning comes into play, which offers a modularized way to build complex applications. So with composable machine learning, one can expect to like build AI solutions more easily, just like pick and choose. Say to experience, right? Given based on the problem nature, we have this we can incorporate different type of experiences, and the models can be of different architectures, and we can like specify solutions for different tasks: classification, regression, generation, or scientific discovery. So with this, we stop like writing one-off code again and again, and we can deliver more reliable and easier to debug implementations, and easier to like onboard new developers. So mapping back to the running example, right, guided by the this concept, the pipeline can be divided into different parts, as I mentioned. The experience part for data processing, for experience handling, and the model architecture part to build models of different structures, and then the loss functions and the training. So let's look at each of these components one by one on basis of this one example. So yeah, besides, as we can see, besides the key components like model architecture, loss functions, which include like divergence and experience, as we see in our standard equation, and the optimization, there is another key ingredient, the operation. And the least components operation, as I will show later, is a key component that provide the interface between the architecture and the learning process. Yeah, so let's first visit model architectures. So yeah, model architectures, as Eric mentioned, there have been like a lot of like studies and huge progresses in like designing very advanced and effective architectures in neural networks, or like more classical graphical models, and even like compositional architectures. So in terms of the neural network design, let's use this text generation or machine translation as the running case. So the very basic architecture in machine translation is the language model. A language model basically calculates the probability of a sentence, given a sentence y consisting of a sequence of tokens y1, y2 to yt. A language model basically defines the probability of the sentence, and this distribution is decomposed across the time steps, one token for one time step. And the distribution of each token at time t, yt, is conditioning on all previous tokens. Okay, so, and to implement this definition, right, this mathematical definition, there can be different choices of architectures. One of the most popular implementation of language model is LSTM recurrent networks. Right? Each of the conditional distribution is captured, modeled by a LSTM cell, basically. Or another emerging application is the emerging architecture is the transformer based on the multi-head self-attention mechanism, and this architecture nowadays has delivered many state-of-the-art results for people like familiar with BERT, GPT-3 or GPT-2. Right? These different very successful models are all based on the transformer architecture. And the next, to use language model in actual tasks is often necessary to condition the language model to some input, also known as the context, so that one can generate the text about the input. For example, in machine translation, right? We will condition the language model on the source sentence, and then we can generate a translation of the source sentence. And say in medical image report generation, the context is then the input radiological image, and we generate the report to describe the image. So mathematically, these distributions are additionally conditioning on the context X. And then in terms of the architecture, right, the previous machine language model architecture, such as transformer, now become a submodule called a decoder. And we will be using an additional component encoder to encode the input context into the feature vector, which is then fed into the decoder. So we get an encoder-decoder architecture. Yeah, so we have seen this encoder-decoder architecture for conditional generation, say machine translation. And there are many other different tasks, right? Say in NLP alone, there are tasks like named entity recognition, NER for short, and like sentiment classification, which is basically a classification problem. Given an input, the output is a single label. And in NER, named entity recognition is more like a sequence tagging problem or sequence classification problem. For each of the tokens in the input sentence, we will predict a label for it to basically saying like whether this token belong to a particular entity dimension. So there are different natures of tasks, classification, sequence classification, or sequence to sequence. And all these different tasks can be further decomposed or be implemented using different architectures. Like we use classifiers for classification, sequence classifier or sequence tagger for like the task like an ER. And usually we'll use an encoder, right, to first encode the input raw text or data into a feature vector, and then say we stack a classifier on top of the features to create the final classification label. And further, this classifier or sequence classifier or encoder decoder can be decomposed into more elementary components like feed-forward neural networks, which is usually used for classification or like sequence classifier, or like recurrent networks of transformers as an encoder decoder. And we can do this even further. Like recurrent networks is usually consisting of like different cells, right? LSTM cell, GRU cells, and usually in combination with different attention mechanisms. And say transformers is essentially a stack of multi-head attention components. Yeah, so basically we get this hierarchy or graph of architectural components, where components can be reused in multiple higher level components. And as we said, there are a lot of like progresses in the research of neural architectures. Say in the past 5 to 10 years, for like image classification, there are a lot of like variants of convolutional networks with increasing depths of the networks and the more complex neural network topology. Yeah, so besides neural networks, probabilistic graphical models kind of stand for another category of like model architecture design, which is particularly useful to specify structures between different variables in a problem. And there are enormous research on the model architectures, like say starting with the most basic naive Bayes, right? We can extend it to be like hidden Markov neural networks, hidden Markov networks to model the sequence data, or like more generally generative directed map models. Or we can design the architecture in a conditional model fashion to get a logistic regression, or like a conditional random field, CRF, for sequence or like more general graph modeling. I won't dive into more details here, but basically we have a lot of like different choices in this model architecture design. And with all these components, one can further compose many more complex architectures, like composite both like these probabilistic graphical model components and neural networks. Like say in architecture B, right? It's basically a probabilistic variational encoder decoder, with both encoder and decoders implemented as neural networks. And say in architecture F is basically a kind of like a model with cyclic components that you predict y, give the result y, given the input z, and you use another component to try to recover the input so that you get this cyclic feedback in the model. Okay, so we have seen the examples of architectures and the breakdown and the compositions. So next, let's visit this other parts, essentially for enabling the training of the model, including the optimization, the loss functions, and the operation. So the first, the most popular learning paradigm, right? We see examples of learning from data instances. Yeah, with this encoder decoder, right, for machine translation, the experience we usually use is a collection of data instances, X star, Y star, and the divergence, right, is cross entropy, right, as we see in the first part of the tutorial. And this basically reduces to the maximum likelihood estimation, resulting in this very simple loss function. And here, one thing to be kind of like pay attention here is that the operation, basically, with this encoder decoder architecture, how do we use this architecture to like compute this loss, to do the inference, right? We evaluate the loss function and to drive the training of the model. This involves the operation on the basis of the architecture. So here in particular, with this maximum likelihood estimation, the particular operation we use is usually called the operation called the teacher forcing decoding. So in this decoding strategy, for each time step t, we feed in the model the previous ground truth tokens, y star basically, to decode the next step. Right. So so that we get the sample that depending on the previous ground truth tokens. And then with this operation, we evaluate the loss and we do the optimization. Basically, the optimization of the loss is pretty simple: stochastic gradient descent, kind of like a reduced form of the EM algorithm derived from the standard equation. And then another second type of experience we could use in addition to data examples is the adversaries. Yeah, so here we have an adversary called also called discriminator, right? I think in games, basically the discriminator takes as input the sampled text y hat, and then the true data examples, and the discriminator can tell like which one is true and which one is like alternative samples. And here divergence, as we mentioned earlier, it can be like different forms of like divergence measures. And again, this operation is different, becomes different given the loss function and the different experiences. So here we see that from the figure, right? From the architecture, we want to basically backpropagate the gradient from the discriminator back to the decoder to like update the parameters in the decoder. So but the text samples are discrete, right? The sample y hat is discrete, which prevents this gradient backpropagation. So here in this operation, it's necessary to do some approximation. Basically, we need to use a different decoding strategy compared to the teacher forcing decoding in the maximum likelihood estimation. So in this so-called gamble softmax decoding, we use a differentiable approximation of the samples y hat for gradient backpropagation. Basically, we use the softmax probability distribution as a representation of a discrete token. Okay, and then optimization, we have seen this. We can use like probabilistic functional descent with convex duality to make this optimization efficient. And basically, we recover the game models, basically. Yeah, and the third type of major learning algorithm or like type of experiences we can use in machine translation or in text generation in general is the reward function. So the experience becomes like data instances plus reward metrics like blue score. So the blue score basically take as inputs the sample y hat and the real data y star, and returns a score measuring how good this basically measures the lexical overlap between the sample and the true data as a kind of like a score measuring the quality of the output. And the divergence is cross HB. And here, the operation becomes very flexible as long as the decoding strategy can produce whatever samples, like translated sentence samples. We can use this operation to evaluate this the loss function. And here, the decodings can be like greedy decoding, sampling decoding, or bin search decoding, or like top K, top P decoding. Yeah, so the optimization is basically the expectation maximization, right? As derived from the standard equation. In the each step, we basically do the policy evaluation, or as inferring the quality of the current model status based on the generated samples, and then we use M step to perform the optimization in terms with regard to the model parameters. Okay, so we have seen these different components with concrete examples, and we see that different components can be of many different choices. Yeah, so even further, like here, basically decoders can be with different like architectures can perform all these different operations. In the text generation setting is the decoding strategies, right? Like teacher forcing and like gamble softmax and sample decoding, all these different strategies. And this decoding, the choice of this decoding will depend on what kind of experiences we'll use. Like if we use data examples to do this kind of like supervised learning, we use like teacher forcing decoding. And saying the virtual training, we use like gamble softmax as one of the choices. So as we can see here, right, there is a very large number of combinations of architecture, operation, loss function, including the experience and the divergence, and also the optimization. So it's basically impossible to enumerate all of these available configurations. It's thus very necessary to like properly decouple them, all these components, with a very clear interface, so that we have like managing the complexity, implementing all these different algorithms and the modelings. So the interface is essentially like this, which kind of like already becomes obvious given my presentation of this text generation example. Basically, the first is that all architectures should expose a uniform interfaces for specifying one of the tens of different operations to generate the samples, or like infer any like quantities. And the training algorithm, the training procedure, including the loss function evaluation and optimization, will repeatedly call this arbitrary specified operation procedure during the training process. So the operation is kind of a subroutine included in the optimization loop. And with this interface, basically the training process is totally agnostic to the model architecture. So that you can basically plug whatever of model architectures, neural networks, graphical models, neural networks with different like decoder structures into the loss function, and then we do the optimization regardless of what architecture you use. Right. So this is a concept of composable machine learning. With this concept, like basically like we use basic musical notes for complex machine learning systems, and we have certain like structure or rules for combining these nodes into like rhythms or chords, and we at the end we get these compositions. So next, I'm going to show you how these concepts really guide us to implement, to deliver a true kind of actual tool, machine learning tool, to enable this machine learning composition. So here we come to Texer, a open source machine learning toolkit for composing your machine learning applications, just like playing building blocks. Okay, so yeah, we have seen this kind of like architecture decomposition, right, as a hierarchy or like a taxonomy. And this basically gives us a conceptual understanding of this the landscape of machine learning. And then Texer basically transfer this or operationalize this into the actual implementation. Yeah, so Texer basically delivers such a stack consisting of a bunch of like different categories of modules, like the model architectures, the loss functions, and like the data processing or experience processing, and the optimization basically trainers. And here is a kind of a more like a detailed catalog of the text modules, like say in encoder, right, as we just saw, like we have different choices, directional recurrent network encoder, or hierarchical encoder, or convolutional encoder. And for decoder, we have like transformers, recurrent decoders with different attention mechanisms, all these different choices. So users can like assemble all these different components, pick it from the catalog, and compose the complex applications of interest. So Texer highlights the three key aspects. The first is the modularized. So that users can assemble any complex models like playing building blocks. And it is designed to be versatile to like support a large variety of models, algorithms, and applications. And this is essentially enabled by this actually the modularized design, because like with this modularization, we have very managed complexity of the library, so that many of the components can be reused, and we have like control the number of components, but you can like essentially build whatever models you want. And the Texer is also designed to be very extensible, so that users is allowed to plug in any customized or like external components into the library. So now let's see how Texer can actually implement a solution. Again, we use the running example machine translation to showcase this. So the first step, as shown in the pipeline, right? We want basically process the data or experience. And here we first start with learning from data instances. So we have this data, right? Input is a sentence, and output is the targeted sentence, a translation of the input sentence. And we have this data sets. Yeah, so then we start like this implementation. With Texer, the first step is to load the data and do necessary pre-processing. And yeah, it suffices to like make by making just 2 function calls, the data module automatically does many standardized processing according to the configuration dictionary specified by the user. So the typical processing steps, including like data reading by specifying the data file names, and like do truncation if we specify the maximum sequence names. And we add special anchor tokens like end of the sentence or like the start of the sentence, so that the model can recognize like what is like a complete sentence basically. And we can do like random shuffling of the data or like automatic batching. Right. And then we built the model architectures and the inference or like the operation, the decoding operations. So we first built a word embedder to embed discrete text into the continuous word embedding. Again, users can like provide the configure dictionary to like specify the hyperparameters, such as the embedding dimension and how the embedding parameters are initialized and regularized, etc. And then we need the encoder to encode the word embeddings into a higher level feature factor. Here we use a transformer encoder with the hyperparameter configuration like this, where we can like configure different options like the number of blocks, which is the number of layers basically, and the number of heads in the multi-head attention, and several other dimensions. And then we use the encoder to like take as inputs the embedded sentence and some other meta information like the length of the sentence, and gets the output of the encoder, which is basically the embedded features. Then we can build the decoder, right? By basically stacking. Say here we use the attention recurrent network decoder. By feeding the encoder's output, the features, as the memory for the decoder to attend over, and then with necessary hyperparameter configurations. And then we use the we call the teacher forcing decoding to like do this operation, right, to infer the outputs, including the logics and a couple other quantities. Then we are ready, right, with the we are ready to evaluate the loss function and do the learning, right, based on the output by the operation. Here we use the cross entropy loss. Again, we use a single API core to like implement this loss evaluation. And here we omit the optimization procedure, which is also pretty standardized with the Texter APIs. Yeah. So yeah, here is a very quick demo on like show how this actual code work on the server. So here is the data config we use specify how data is processed, and then the config of the model, including the encoder, decoders. Yeah, we run this training and evaluation by feeding the configure files. And this is kind of like on a trial data example, trial data set, so that the training is pretty fast, and you can see that the training progresses basically. Yeah, and after training, we load the model and do the actual inference, like prediction on test data. Yeah, this is a pretty simple example showing one of the actual implementations supported by Texter. And basically you can see like within 20 lines of code, we essentially built the machine translation model very quickly. And recall that in the code example, we use the data instances as the experience to drive the learning, and they use like teacher forcing decoding and cross entropy loss. And now suppose that we want to switch to use other experiences given the kind of like available experiences in the problem, or maybe like we want to like try to devise a more advanced algorithm to train the machine translation model. To switch to a different experience, one only have to like change the small portion of relevant code while keeping all other parts like data and the model architectures untouched. This is basically the essential advantage of the composable machine learning concept, right? So here, say that we want to switch to use reward and the data instances. then we only need to like change this particular portion of the original code. Right here, we essentially now use a random sampling decoding to get the sample. Right so the operation is the sample decoding instead of the teacher forcing decoding. And then we do this learning, right, based on the operation results. Here, our Texter provides a kind of a high-level interface to enable this basically reinforcement learning. Here we use policy gradient agent for training, and it basically involves a loop, right? At each iteration, we first get a sample using the operation random sample decoding, and then we evaluate the reward, the blue score, and then we do the basically M step in the EM algorithm to update the model parameters. And then similarly, say we want to use an adversary, right, instead of a reward function to do the training. Again, this is pretty simple by changing the particular part of the original code. So the operation, as we mentioned, now we will be using a Gamble softmax decoding as a kind of soft approximation to the discrete text samples, so that the visual learning can backpropagate the gradient from the discriminator to the generator, to the decoder. So then with the Gamble softmax decoding outputs, we additionally construct the discriminator, the adversary, as a kind of convolutional classifier in this case, and then we evaluate the loss. Yeah, so a very quick summary of machine translation in text. Right? This very modularized programming. We have experience, we build the model architectures, and then perform the operation to get the decoding results, and which is then used to evaluate the loss function and perform optimization. So all these steps are completed with intuitive conceptual level APIs. And with the composable machine learning design, we can easily switch between different forms of experiences by plugging and out modules and keep other irrelevant parts unchanged. So applications of text besides machine translation and the controllable text generation we have seen at the beginning of this part, Texter has been used to produce many other like products in practice. So let's say Forte is a more complex, higher level library built upon Texter to support complex natural language workflows. Like say you want to build a knowledge graph out of a COVID-19 corpus. Right. So this whole process, the whole pipeline will include a lot of like NLP tasks and components, basically. Like say, given a piece of like literature reporting COVID-19, you will first extract the named entities from this raw text, right, using NER models. And then we will extract the relations between these entities using relation extractor in NLP. And then we will do like other like analysis, like a coreference resolution to like consolidate different entities together and basically group these different dimensions so that we have a kind of like more consolidated view of these different mentions entities in the whole corpus. And there are a lot of other different components. And at the end, after building the knowledge graph, we may want to like build a question answering engine right on top of this knowledge graph, so that a user can easily input any question about COVID-19, and the question answering engine can like pick the answer from the knowledge graph or from the original raw text corpus. So all this, so we can see the workflow will involve all these different components in NLP. And the Forte basically provides this infrastructure for this interoperation between different components. And these more details will be presented by Qilong in the third part about Forte. Yeah, and yeah, Tensor is also used to like build this chest X-ray image report generation, as we have seen on the whole architecture. Right, we have seen this in the beginning of the talk. And yeah, there are other things like chatbots with multilingual cognitive ability, all these different applications. So here is a kind of like a architectural implementation of this report generation, where we can see there are a lot of different components, like raw data enrichment to create this extract different features, both like visual and textual features, and the report generation module to like basically generates the very lengthy reports in a hierarchical manner. We first generate the topic of each of the sentences in the report, and then we entail this topic into like concrete sequence of tokens for each of the sentences. So at the end, we get the whole paragraph describing the input image, and then a lot of like post-processing steps like machine translation and text analysis to visualize and make the report more structured. So here is a very quick demo on the resulting application of chest X-ray report generation with translation. Let me see if it's working. Okay, so it's kind of like stuck here. So maybe we can move on. Okay, so yeah, besides this composable, the overall composable machine learning kind of support of Tensor, another key feature supported by Tensor is the transfer learning enabled by very large pre-trained models like BERT, GPT-2, GPT-3, or like Elmo, right, for like text embedding. So these pre-trained models serve as critical components to like compose very powerful models in different end tasks. So yeah, so basically the concept here is that we first pre-train the new models, right, on massive data, and then we use this as the building blocks to build construct downstream models for different tasks, and we fine-tune the whole model on downstream application, downstream experiences. So like here in this BERT-based classification, we can implement with Tensor using a couple of lines of code. We can first build the BERT encoder and then stack a classifier on top of it, or like directly build the BERT classifier. And yes, Tensor supports both TensorFlow and PyTorch to like basically integrate the advantages of both libraries. Say TensorFlow provides this static programming paradigm, and with very rich surfing functionalities and mobile support. Yeah, and PyTorch gives this dynamic, more intuitive dynamic programming interface with easy editing and debugging abilities. So Tensor basically provides the same comprehensive support of machine learning functionalities on both platforms, and is fully compatible with the native TensorFlow and PyTorch APIs. And these are the resources of Tensor, including the websites, GitHub with code, and a lot of examples and documentations. So there's a broad spectrum of open source machine learning tools, ranging from like general tools with low-level APIs, such as PyTorch, TensorFlow, and even Keras, to like more domain-specific tools with high-level APIs, such as NLP tools like NLP plug-in phase transformers, and for other applications like reinforcement learning. So there is usually a trade-off between API usability and compositionality, or customizability. So Tensor works around this trade-off by providing interfaces at multiple abstraction levels so that the tool is friendly to both novice and experts. Yeah, so as I mentioned, like transformers, right, provides these high-level APIs to basically support the state-of-art pre-trained transformer models, and likewise. And these tools basically provide these composable machine learning functionalities to an extent, and the Tensor base integrates all these more of the advantages to support this solution composition in a more efficient way. Yeah, so I'm gonna wrap up here for the second part. We talked about machine learning solution design with this standard equation interface by plugging upstream available experiences into learning, basically designing the F function, the experience function. And we discussed the tooling for compositionality in machine learning with the interfaces and the composition between architectures, operations, laws, and optimization. And the Tensor is a library that really implements its functionalities. Okay, so I'm happy to take a couple of questions if we have any questions, and then we can head into a 10 minutes break, basically. Yeah, if you have any questions, please feel free to post in the Zoom chat box. Great, I guess so far so good. Yeah, I think we can probably take maybe 5 minutes break because of the time constraints, and then Qilong will take over for the third part about the computing infrastructure, including like interoperation, automatic tuning, scheduling, and training. Yeah. Stop sharing. Yeah, let's have a break and see you all at around 4:15.
Okay, it is now 3:15. Hope everyone had a good break there. We're coming to the last part of the tutorial. Thank you, Eric and Zhiting, for the presentations on part 1 and part 2. Let me share my screen here. Okay, bring this into full screen. All right. So in this third part, I want to talk a little about the what I call the infrastructure AI support for AI, the support that's needed to back up the standard equation, which we talked about in part 1, which is kind of like a mathematical standardization of many different AI tasks and problems. And then we also talked about learning with all of experiences and the composition that was enabled by the TechSAR, which is a software system with libraries that allow you to put together the programs that take these experiences and then realize them in the form of models. But then what about the systems that go below the models, the learning and the standard equation, the infrastructure that's needed for productive ML to support doing machine learning at scale, doing it in an interoperable fashion, and I'll define what that means in a little bit. These to us, I think, are represented by the 4 points: interoperation, automatic tuning, distributing, and scheduling. And why do we need these? So if we look at using NLP as an example to explain how complex AI tasks have become these days, right? If we want to take many different complex experiences, putting it into the experience part of the standard equation, there's many aspects that go beyond a single model and may involve multiple models. For example, in NLP, you might have different stages for text processing. Typical application might start, say, searching a document. You might want to retrieve and analyze the top results. You might want to generate answers based on the finding. And that's a very maybe simple information retrieval case. But what if we want to take it to a different level? For example, processing that's at the morphology level, right? Standardizing words to their root words, performing the syntax level analysis, or even the semantic or pragmatic level analysis. So there's quite a diversity of tasks, and this is just within NLP, without even getting into the other domains of machine learning, such as computer vision and time series analysis. So building a general platform for NLP is challenging because you need to take these experiences and you need to be able to create a system that interoperates between the parts at these different levels, right? And this can be accomplished with, I think, the right productivity tools from learning from experiences at scale, which ultimately boils it down to the right set of libraries, which can be expressed in a few short lines of code, as well as a set of visualization tools that makes it possible to understand what is happening inside the data, right? And we think about this as the word I'm going to use is a workflow. A workflow basically converts the real world problem of getting multiple experiences into something that's more organized and can be expressed as code. So with that out of the way, I want to talk a little bit about, maybe dive a little deeper into explore the stack of the systems that support modeling and learning. Starting with interoperation, I'll talk about an open source system that we have called Forte, and coming down to automatic tuning, automatic distribution over multiple machines, and automatic scheduling of workloads. So beginning with Forte, what is Forte? It's, we like to call it a scaffold for larger NLP applications and workflows, a way to integrate different types of experience into a single workflow by allowing this interoperation between data and model. In the Forte software system, there are multiple modules, such as a machine translation module, analysis modules for sentiment classification, parsing, name entity tagging, and many others, such as document retrieval. Just as a developer might use TechSAR, we talked about earlier, to implement some of these models individually, these models can then be plugged into the Forte scaffolding in order to interface between the different modules. Like, for example, you need to first take the data, you need to validate it, you need to embed it, you need to translate the results from one module to another, right? And that is something that we accomplish by organizing NLP tasks into 3 major types of structures. One type of structure is the sequence structure. for example, in sequence structures, you might talk about lemmatization or stemming, which is to convert words into a more standard representation, adjustable to adjust, better to good, and formality to formal, for instance, right? And then we also have the cluster structures, which is for entities like entity coreference, trying to understand if the words I and he refer to a particular name in a sentence, or who's the speaker and who's the reference inside the sentence. That's the cluster structure. And tree structures come about when we talk about syntax parsing, discourse parsing, right? And at these three different structures, by categorizing different NLP tasks into each of these structures, we can plug in the different models that are created in Tensor or in other systems and get them to interoperate with each other. So architecturally, Forte starts with a carefully designed data representation used to represent a variety of tasks. And on top of the scaffold, we organize different levels of models and knowledge, starting with a ML library that's powered by systems like Tensor, going up to pre-trained models, fine-tuning the models, and incorporating domain knowledge. Complementing the Forte system is an interface we call Stave. It's a tool that visualizes different text analysis results and allows for what we call human-computer collaboration. It's a way, for example, for humans to, a simple example is to maybe label the data that comes in, an unsupervised piece of data, and it needs to be labeled in order to perform, say, parsing, for instance. But it can be used to do more than just that. And I'll talk about an example in just a little bit. Now, as a whole picture, Forte and Stave together, we want to present an infrastructure that helps make the different components reusable, organized, and into a standardized workflow construction, starting with the data representation, performing workflow control, which is how the data moves from stage to stage, along with the actual machine learning modules that perform retrieval, analysis, and text generation. Let's show a little bit of a code example how Forte and Stave work together. So imagine we're trying to build a clinical data management system. That was kind of the video that Zhiting was trying to show a little earlier, although there was a bit of a technical problem. So in Forte, you would declare a pipeline object, and it's as simple as adding different components, different modules into this pipeline, starting with a reader to ingest the data, followed by an information extractor for name entity recognition, for relationship extraction. And then this entire block of code here can be, on top of it, you add an indexer to index different results and construct a pipeline. And what this gets you in about 15 lines of code is this a system to analyze and conduct information extraction from documents and then index those documents in a way that can be retrieved by the information retrieval system. So then how do we actually use that? Taking the pipeline as an example, it just takes a few commands to perform reading the user input and query it against the index. So that's basically a search, and then to perform the retrieval. And this can be called even from, for example, front ends, such as the Stave graphical front end is integrated with Forte in order to call it to perform the retrieval that's then displayed inside the Stave interface for further annotation or for human computer feedback. So the point about Forte and Stave is that it provides the scaffolding that enables users to construct a NLP workflow in a reasonable number of lines. And under each of these operations and functions, one can plug in either, for example, a model that's implemented in Tensor, or perhaps other models that are implemented in the other systems that Forte supports, which if we were to go back a few lines, includes, for example, the LN NLP library, different PyTorch libraries, different TensorFlow libraries. So moving back, let's talk a little bit about automatic tuning next. So if Forte provides, for example, the way to incorporate multiple experiences from multiple models using libraries like Tensor, then we now get down to the kind of practical aspect of how do we train machine learning models? How do we apply basically training or learning algorithms to the standard equation in order to, for example, get the task performance or any other metric that's kind of desired by the machine learning user. How do we get that to be improved? And in particular, the subject of auto-tuning or just tuning in general is about how we do this beyond what a machine learning learning or training algorithm, which only optimizes the parameters of the model theta, can do. So for tuning, there's two types of tuning in the world, or at least it's currently categorized that way. One is hyperparameter optimization, which applies to the kinds of loss function coefficients, which are Euclidean or integral quantities in the elements of Q, E, D, and H in the standard equation. Basically anything that's not the parameters theta, which are the target of a learning or training algorithm. It also includes quantities that don't even show up in the standard equation. For example, when you perform the minimization, the SE, you'd like to maybe apply a algorithm. Maybe you're applying a basic stochastic gradient descent. Perhaps you'd like to apply an optimizer like an atom or something that uses momentum or acceleration. Many different optimizers exist and they have their own magic numbers of tuning parameters or hyperparameters. Auto-tuning also involves how to select these quantities in order to improve a task performance or other metric. So this kind of hyperparameter optimization is standard practice for most deep learning and machine learning models. We also have neural architecture search, which is kind of like seen as a maybe broadening the scope of tuning to apply to not just the Euclidean integral vector or matrix quantities inside the standard equation, but to the actual terms that represent neural network layer structures, layer sizes, layer types, multi-layer architecture subgraphs. This can be thought of as rewriting the Q and P inside the standard equation. It's a technique that's a lot of research has been invested into, promising but not quite mainstream. But we'll see a little bit how that can be rolled into a single integrated system using Bayesian optimization. But first, before we do that, why would we want to do auto-tuning in the first place, given that perhaps many of us as ML practitioners are familiar with hand-tuning models? Well, auto-tuning aims to make the tuning process trustable in the sense that the HPO algorithms, such as Bayesian optimization, have theoretical justifications and guarantees behind them. Just as importantly, it needs to be consistent. You want the result of the tuning to be repeatable for responsible and ethical machine learning. And so given that different human practitioners will tune things in slightly different ways, you really want to get this to be repeatable so it can be trusted by society. Just as importantly, you want to save human effort. Any type of effective tuning usually requires setting up dozens to hundreds of trials, and that takes a lot of, that's a productivity question that should be answered by automatic software. And finally, principled methods that perform hyperparameter optimization in a sequential fashion, such as Bayesian optimization, can be a lot less costly than manual tuning. Whereas in a manual tuning scenario, you might select some number of points based on intuition or guidance, or maybe in a more principled way, you might do a grid search. Methods like Bayesian optimization and HPO tune the model one trial at a time and use the information from earlier trials to decide where to search next. And that can result in fewer trials, leading to computation and cost savings. Okay. So if the goal of hyperparameter optimization is intuitively to improve task performance or any other metric, more formally, we can say that it finds a point in a search domain that best optimizes the objective using the least cost, fewest number of queries, right? So domain meaning the search space. It could be the range of different hyperparameters as defined in the earlier slide. It could be a set of neural architectures, basically different ways of writing the terms Q and P inside the standard equation. A query is basically an evaluation where we train a model for a given set of hyperparameters or a given architecture. It comes back with a task performance. Maybe it's 80% accuracy, maybe it's 90% accuracy. That's of course costly. And the objective we want to achieve is to improve the accuracy, the error of the model, the validation data set, as an example. So some of the basics around HPO include popular techniques include grid search, exhaustive search, random sweeping over a set of parameters. You could also add some stochasticity by making it random, by doing a random search or random sampling. But we'll focus a little bit more on methods that are sequential in nature, such as Bayesian optimization, where earlier queries influence in a hopefully productive way the later queries in the search so that it converges to a good set of parameters faster. So in model-based optimization, such as Bayesian optimization, we're going to use a probabilistic model to intelligently plan queries and perform efficient optimization. So for a sequence of steps, Bayesian optimization basically defines an acquisition function. That's just a way of saying this is the function that picks the next point in the hyperparameter space to search. And then often that's done by training a predictive model on data so far. For example, if I knew that with a learning rate of say 0.1 and maybe a momentum of 5.0, I would get a certain accuracy, I can input that into my model and use that as a data point to train a model that predicts where the next set of hyperparameters, what kind of performance, task performance is going to achieve. And essentially Bayesian optimization is a loop where you try to optimize this acquisition function. You put a query in X, which is the set of hyperparameters, you observe the result and you update the model. And over time, you refine this predictive model in the hopes of climbing up this hill of task performance and eventually reaching an optimum. Now, so those were the basic principles of model-based optimization. And what we want to create is a composable system that allows us to treat in a kind of a black box fashion with no matter where you produce the model, whether it's from a modeling framework like TensorFlow or PyTorch, or more specialized language like say probabilistic Bayesian languages, for example, like Stan, or for example, any type of model library, or even a composable system like TextSub. We want to make sure that we can put in any type of model and be able to optimize on it as if it were, I don't use this word lightly, but think of it as basically a black box interface where you can just put in a model, and as long as you can get a result from it, Bayesian optimization will help you find a better point in the hyperparameter space. On top of that, so we have developed a system to complement the other open source systems that we've created called Tune, which is it implements Bayesian optimization for neural architecture search. It's compatible with, for example, probabilistic programming languages, but more generally, it's also compatible with the wider span of deep learning models that may not necessarily have a Bayesian or probabilistic interpretation. And in this search system, it's able to search not just for hyperparameters, but also different model architectures. That's to say, different combinations of layers or different combinations of variables inside a Bayesian's or a graphical model kind of system. And the way you write code in Tune, this system that we created, is pretty simple. You write down a function to be optimized, you define the domain of parameters that you need to search over, and you write down these are Bayesian optimization concepts, acquisition function, which is kind of how do you predict the performance of a set of hyperparameters, right? And then there are different optimizers that I won't go into detail of, but you can plug in to compose your own hyperparameter tuning experiment. And then finally run the Bayesian optimization routine to do that. So this can be done in less than 20 lines of code. And the point of the design here is really to allow the use of hyperparameter tuning across a range of different backends, across a range of different modeling frameworks and optimization packages. This interoperation is crucial in our view because that provides a one-stop shop for users to be able to plug in different models, again, using their choice of framework, using their choice of optimization package. So with that, I'm going to move on to the next section, which is automatic distributing with another open source package we call AutoDist. So what AutoDist performs what we call distributed ML training, and that's the use of multiple machines to finish learning or training an algorithm more quickly. And it's also used to enable the training of models that are too large to fit onto one machine. Now, people may sometimes ask, well, why do I need to use multiple machines? It's expensive to acquire them. I have to go on maybe AWS to use them. I have to get cluster resources. Why can't I just stick to using one machine? So the most obvious use case is when, well, the model's too large to train on one machine, and you have to do, for example, through model parallelism, splitting the model over multiple machines so it will even fit in the memory to be trained. But I also want to make a case for why finishing the learning or training algorithm faster is actually becoming more and more important. So, for example, if your model may have taken 2 weeks to train, then the natural question to ask is, wouldn't you be more productive if you could train it in a few hours? And let's say you have a model that does train in a few hours, right? It really trains quickly enough. If you want to get good task performance, you want to apply an automatic hyperparameter tuning on neural architecture search system to push that performance even further. And that's going to take 10, maybe 100 plus trials. And frankly, even if you didn't do this automatically, you'd probably still have to do this manually. So you don't want to discount the fact that you need to do this multiple times. And then this comes to an interesting question that if I'm going to do tuning, maybe I could just do a naive parallel grid search, right? It's easy for me to say, hey, I searched these 10 different learning rates times these 10 different other hyperparameters. And maybe that will work, but I think the important message is that this is actually quite wasteful, and that sequential or model-based optimization methods like Bayesian opt can do this with a lot fewer trials. Now, because the trials are sequential, you can only do them one at a time or a few at a time. You need them to complete quickly, and this is where distributed ML comes in. So rather than running, say, 100 different very cheap trials at once, you could run 10 more expensive trials at the same time, but have each of them complete faster. More expensive in the sense that they're using more machines, but completing, say, 10 times as fast. Okay. Now, if we believe that distributed ML is the right tool for productivity, then we can ask ourselves some questions like, why is it that it's not very popular right now? Why is it seems that it's kind of difficult to use? And that's because deep learning is, especially deep learning, which is one of the major ways of incorporating experience into the standard equation. It's diverse with a highly variable architecture. So architectures. So when a new model architecture emerges, say from convolutional layers to recurrent layers to transformer layers, or even other types of layers that have yet to be invented, it's often the case that we have to design another system to scale it effectively. And that results in a situation where there are separate code bases and APIs with a kind of minimum interoperability. Some names that have come up in the past few years include systems like Horovod, Boson, BytePS, Orpheus, deep compression systems. Each of these excels at a different type of architecture or at a different type of layer. But in order to use them, you have to learn different APIs and interfaces. With, for example, mesh TensorFlow, you have to learn how to write a partitioning layout on mesh. With other systems, you might have to supply the mapping between operators and devices. You might have to hack into the optimizer. You might even have to perform some calculations on gradients to pass them around to the optimization system. And all of that's a lot of different code to learn. So what if we could adopt a different kind of interface? What if we could present users with just a single interface that allows you to use all of these different strategies from one place? A compiler that will just ask the user, hey, what strategy do you want to use? Do you want to use all reduce? Do you want to use a parameter server? And I'll go create all of the nitty-gritty low-level work of writing the code that makes the correct strategy work. So that's what we mean by a compiler. And that comes about with a level where you specify a strategy, and then that strategy is converted into different kernels, and that's sent to a coordinator that runs it on other interoperability, other software that we interoperate with, such as TensorFlow, such as PyTorch. And the reason for that is to turn the whole space of different distributed ML strategies that have been written across different papers and systems into a single system that just unifies the representations of these parallelisms and composes them together, which enables Autodisk, an open source system that's already on our GitHub, to take the place of multiple systems such as Horovod, Boson, BytePS, and Poseidon, replacing all of them with a single system that all you have to supply is models, machines, and, for example, an instruction on what strategy to use, and it produces the distributed training strategy and then calls TensorFlow or PyTorch to execute them. So what can you achieve with this? You could achieve the common data parallel type of strategies. You could achieve model parallel strategies where the model variables or the data flow graph in these systems is partitioned across different nodes. But even more interestingly, you can create a hybrid or adaptive parallelism that perhaps I would say maybe the convolutional layers of this model we should use a deep compression on them. But then on the fully connected layer, maybe I'm going to use a sparsity aware strategy on this, right? So the possibility here is to take a complex architecture, which comes about from complex experiences being put in the standard equation, and being able to compose and apply the right distributed technique for the right layer. So how then do we use this? Well, option one is I could pick from a library of well-known strategies, parameter scalar strategies, all reduce, sufficient factor aware training, sparsity aware training. By specifying that, all I have to do is take my model training code, put in a few lines of import and a little bit of boilerplate to choose strategy and construct the object, and create a session at the end so that Autodisk can read in the information that's going to TensorFlow. And then all you have to do is select a strategy builder, which takes maybe a few more lines of code. The strategy builder tells Autodisk what strategy am I going to apply, based on my expert knowledge. That I know this is a convolutional network, so maybe certain techniques I should use, or maybe this is a transformer network, so I want to use another set of techniques. And then all you have to do is add in a few different lines to specify what strategy you need. And what Autodisk does is it takes care of building the entire network topology. It takes care of building the operator graph. It takes care of all of the low-level transformation using kernels in order to make the strategy apply to a model. And that's only just a tip of the iceberg. Autodisk also allows for automatically composing hybrid strategies that combine one or more of the basic strategies, goes beyond the pre-designed builders, and then to create a strategy that's customized in the sense that different layers could be using different mechanisms, such as all reduce, such as sufficient factors, such as deep compression, such as sparsity aware training. And what that results in is a composed strategy that is unique to your model, and it's created by in fact, quite an interesting problem, how to create such a strategy. And the details are actually under conference review right now. But this is something that we believe it's going to be the future of how people use different distributed systems, and how different systems, the essence of them, the actual strategies behind them, are put into one place in order to enable all strategies to be executed by one system. Finally, last but not least, I'd like to say a few words on automatic scheduling with a system we call AdaptDL. So automatic scheduling has to do with the fact that many ML users, if they have access to, say, a cluster or cloud compute or AWS or any type of multiple environment that has multiple machines, these are usually shared resource environments, which means that you don't have exclusive access to them. You usually have to share them with other users. So many pieces of open source software have been created to manage shared resources in different contexts, such as Hadoop, Kubeflow, OpenStack, and Slurm for general computing. And the reason for doing this is that, well, I mean, it's economics, right? You want to amortize an expensive investment of hardware across users. And you can also make it convenient for the users by providing this software systems that you submit a job and the system goes and figures out how to place that job across different machines. It takes your order and it comes back with the result. But the trade-off for many users, and the frustrating part, admittedly, is that the resources might not be available whenever desired. And so that causes, many people to say, hey, why do I have to use this shared resource environment? Why can't I just do it on my own, local desktop or laptop? Because that's my own resource. It's there whenever I need it, right? Well, earlier we discussed that with auto-tuning and with ever-increasing model sizes, it's inevitable that if you want to stay at the cutting edge of deep learning research in particular, that you have to make use of tuning and distributed learning in order to get the performance and speed that you require, speed of training. And I think rather than saying that, hey, I'm not going to engage with these shared resource environments, how about figuring out how to make this experience better? So let's ask a few questions. What happens when many jobs are run in shared resources, which are created by many users or created by an auto-tuning system that's generating many trials of the same job in order to optimize the task performance? Do we run all these jobs one at a time in sequence? Do we run several in parallel? How do we divide the resources? What happens if I need to change the resources halfway because suddenly I've got, say, an urgent job that's coming in because I need to finish a deadline, for instance? Will that progress be wasted? Well, the first step in automatic scheduling is to enable jobs to not be rigid. Rigid means that a job cannot change the number of resources once it's started. And you can imagine if you're doing a 2-week training on, say, 8 different machines across, say, 64 GPUs, then if I have to interrupt this halfway, that's a very big waste of resources if I have to just stop this. So instead, what we want to do is to allow the jobs to be elastic, which is to say that at any time, the system can change the number of resources. Maybe I need to cut it down from 8 to 4 machines to make room for new jobs, or maybe other jobs completed, so I can go from 8 to 16 machines. This is a kind of an important convenience that users need in order to be able to find that using a shared resource environment is worth it over using, say, their single laptop or machine to do it. The user doesn't specify the resources, but the system tries its best to use as many resources as are available, shrinking or expanding when needed. But even that is not enough to fundamentally solve the problem of resources not being available when desired. In order for people to commit to using a shared resource system, on average, they should have their jobs compute faster than if they were using it using a single laptop or system. And so this leads to a concept called co-adaptive scheduling, where after a resource allocation, you can predict the job scalability of different jobs. So an interesting fact about distributed machine learning is that different jobs have a kind of an upper limit on how many machines or GPUs you can use before they stop scaling well. And you want to be able to figure out what's the maximum number you can use for each job, and then find a resource allocation and a set of tuning parameters such as batch sizes and learning rate, using a metric that we call goodput. It's basically statistical efficiency times the throughput of the system, in order to continually reallocate resources so that the so-called goodput metric of all jobs at once is maximized. And the system that I talked about, AdaptDL, is basically this kind of co-adaptive resource scheduler that does a little bit of profiling in the background, and users only have to spend one-time effort to write a few lines of code to hook the APIs into their training code, and that allows the AdaptDL system to steer the job in the background, taking control of the number of machines and GPUs, batch size, and learning rate. Right? And the consequence of using this is that we can shorten the multi-job completion time. If there's many jobs happening, while I can't guarantee that any single job will finish faster I can't guarantee, for example, that all jobs will finish 3 times faster, but I can guarantee that across all the jobs, the average completion time is between 2 to 3 times faster. And this is possible only because many jobs are being scheduled at the same time, and we're taking a look at what's the scalability limit of each of them, using exactly as many resources as needed to scale the job to its maximum potential, and no more than required. And this basically requires 3 lines of code change. 1 line to enable the adaptive batch sizes, 1 line to enable elastic training in PyTorch, and 1 command to launch on a cluster. So once again, from a productivity standpoint, it's important to make sure that the code modification is as few lines as possible, so people find that the opportunity cost of going to a shared resource environment, which is I have to write more code, I have to give up the guarantee of the job always completing on time, is made up for by, well, it's pretty convenient to be able to submit an big auto-tuning job. Just let the system take care of it. And I know this is going to complete faster than if I were to do this tuning by hand, relying on distributed tuning such as Tune, relying on distribution such as Autodisk, relying on scheduling such as AdaptDL. Okay. All right. I'm going to stop my presentation here. As we are coming to the last 10 minutes, and I'd like to hand over to my other presenters to finish the summary and closing remarks for the tutorial.
Yeah, thanks, Qilong, for the third part. So let me quickly wrap up, please. Yeah, let me wrap up this tutorial with a single page summary. So we have with the goal of learning with all type of experiences, we present the theory of the standard equation that gives us a blueprint of machine learning paradigms to like understand and unify and generalize many of the major machine learning paradigms, which were designed to handle different type of experiences. And with the standard equation, the experience function f encodes different type of experiences in a single uniform format, including like data instances, constraints, informativeness, rewards, adversary models, and so forth. And this standard equation really gives us a turnkey mechanism for like problem solution design by like reducing originally specialized algorithms to other broader contexts, and enable us to like compose experiences in particular problems to deliver the end solution. And on the practical side, we operationalize the concepts and the framework with Tensor to support this composable machine learning. And then in the third part, we discussed computing, including the modern infrastructures of productive ML for automatic tuning, distributing, and scheduling. So I believe this is really an exciting direction to for further study in the future. There are a lot of different things we can explore. We can explore, like say, in terms of this standard equation and the theoretical framework. An interesting question is like how this framework connects to even broader landscape of machine learning, right? As Eric mentioned, like lifelong learning, online learning, or other like meta learning stuff. And also, like from a theoretical point of view, how can we really get a more like rigorous like theoretical understanding of learning with standard equation? Say like given the logical rules, what do we mean by learning with logical rules, right? What's the like the consistency or other like statistical like concept we can use to characterize the learning process? And say every time when we add a new type of experience in the learning system, how can we guarantee that we can get better performance at the end of the day? And in terms of this operationalization, Tensor gives a very good tool for like developers to quickly compose machine learning solutions. Then how can we further instantiate the concept of composable machine learning or the uniform interface provided by the standard equation to really deliver a more advanced and comprehensive toolkit for like end users who may not have any background of machine learning or like even programming, right? And of course, like in the computing side, how can we like further scale up all these development and deployment and automate all the machine learning workflows? So at the very end, I'd like to provide a little bit of food for thought. So we have been talking about this unification, this standardization of different machine learning paradigms, and have a blueprint of the broad context in machine learning. Then the natural question is, how far would the list take us, right? Would the list end up with kind of something in physics, right? People want to like basically integrate or unify everything, every fundamental phenomena in the universe into a single theory, right? So to answer this question, yeah, let's come back to the physics, right? So Phil Anderson, who is a very great particle physicist, once said that physics is the study of symmetry. So by symmetry, we mean like unification and the relations between different concepts in universe. And as we mentioned, the history of theoretical physics research, right? Maxwell's equation unifies the electric and magnetic field, and later on, general relativity by Einstein discovered a relation between gravitation, space, and time. And then we have like standard model that further generalize this theory. And the end goal of theoretical physics research is very clear. It's the theory of everything, using a single theory to explain the fundamental phenomena in the whole universe. Then what about machine learning, right? Is the end goal of machine learning standardization or unification, the so-called, say, master algorithm, that we use a single master algorithm to solve all the problems in the world? Or is it the AGI, right, artificial general intelligence? So in my opinion, these goals are still very elusive and need much work to first clearly defined. But what is really tangible and beneficial starting from now, I think, is the unified way of thinking. With the unified way of thinking, we get a systematic understanding of the whole landscape of machine learning. And based on this, we can devise mechanisms for automated solution creation to different problems in the world. And the end goal is to improve machine learning productivity and especially accessibility to the broader users. Okay, so this is pretty much of this tutorial. We attached, for people who are interested in further reading, we attached some references. And for more resources like the slides and the videos, please visit the tutorial website, and we'll be posting all these resources on the website. Yeah, thanks for attending. Yeah, this is pretty much of this tutorial. Yeah, cool. I think we can wrap up.
A long day. Thanks for those who are sticking around. If you have questions, feel free to ask. I guess you can just unmute and ask verbally to save time of typing. And feel free to also email us and contact us for clarifications or even for codes and for other type of supports. Okay, maybe it seems like we are right on time to wrap up. Zhiting, you want to say a few final words to close this session? In case.
Yeah, I basically want to thank everyone who attends this talk and give all these great questions, and yeah, and thanks. Yeah, thanks everyone.
Thank you, everyone.
Great.
Cool.
Thank you, and hope to have follow-ups down the road. Thank you.
Yeah, cool. Yeah, bye.